which relate the number of cases to the population these cases come from. Some of these clinicians are fully aware of the limitations of the data they are collecting and are interested in the development of cancer registries to address that discrepancy. Other clinicians are not aware of such limitations. L.3.2 Concern about suspected increases in the number of cancers and their potential link with DO. There is concern with the clinical reports of increases in cancers, and the suggestion that this would be due to DO. The Parliament and RS has established a committee to investigate a link with DO and is requesting action by the government to solve the problem. It asked the Ministry of Health for a clarification on this matter. The Minister of Health would like support from international agencies to proceed scientifically and address these claims with adequate methods and come up with a reliable answer. He argued that there is a need to clarify whether there are changes in cancer frequency, and if so their etiology, if from chemicals, food, Chernobyl or other radiation, DO, stress, or a combination of those factors. The Institute of Public Health in FI has similar concerns, as stated in their report on the health status of the population and healthcare system in transition, 2001. The lack of awareness about causes of error in interpretation of clinical findings, and basic epidemiology by some of the clinicians, is contributing to the concern mentioned above as the media reports these both nationally and internationally. There is a good consensus in the behalf of the need to study the matter adequately, and the initiatives to develop cancer registration are a good demonstration of that. L.4 Recommendations 1. Support for the authorities is needed in identifying whether there are any changes in cancers, and to help characterize any such changes, including through the further development and extension of coverage of cancer registers. Existing initiatives on cancer registration, cancer diagnosis and treatment and those to improve estimates of population should continue to be developed and improved. 258. Post-conflict environmental assessment. 2. Support for the authorities is needed in identifying whether there are significant exposures to DO and other war-related environmental risks and, if so, help establish protective measures. 3. Build local capacity in clinical, environmental and cancer epidemiology, and the capacity to interpret health information coming from both clinics and registries. 4. Develop descriptive epidemiological studies to respond to questions of changes in frequency and distribution of cancers in the population. 5. Develop analytical epidemiological studies to investigate the potential contribution of risk factors including environmental risks and DO exposure, as well as other risk factors, to certain types of cancer. 6. The analytical studies mentioned above would require the development of methodologies to estimate exposures to potential risk factors under evaluation that would consider the population moves observed in BH over the relevant time period for those studies. 7. Facilitate the development of cooperation in the above activities between FI and RS researchers and cancer registries, as exchange of information is likely to be necessary to achieve the above goals. Furthermore, studies of rare cancers may require cases from both sides in order to have adequate capacity to respond to the study question. 8. Support for the authorities is needed in the development of a risk communication strategy regarding the measures being taken, and eventual findings. L. WHO Assessment. Depleted uranium in Bosnia and Herzegovina. 259. M. Appendix M. Storage of radioactive waste and depleted uranium residues in Bosnia and Herzegovina. M.1 Introduction. Since 1997, UNEP and the International Atomic Energy Agency, IAEA, have established a good working relationship and have been involved on a number of projects together, including the 2 previous UNEP DO assessments. One of the tasks assigned to the UNEP team for this mission was to conduct an investigation of the regulatory and technical infrastructure the country has in place concerning the storage of radioactive waste and, in particular, DO residues. As part of this task, the IAEA representative, accompanied by an UNEP team member, carried out a series of meetings with national authorities and visited the interim low-level radioactive waste storage facility of the Federation of Bosnia and Herzegovina. This appendix describes the outcome of this investigation. M.2 General Overview of the Radiation Protection Infrastructure and M.2.1 Organizational Infrastructure. At the end of the war, the legal framework in the area of radiation safety was essentially the same as that existing in the former Yugoslavia. The main legal instrument in force was a basic law on protection against ionizing radiation supplemented by a number of regulations. These regulations were produced in 1977 and were inconsistent with most recent international standards, including the IAEA's International Basic Safety Standards, IAEA, 1996. The division of Bosnia and Herzegovina following the Dayton Peace Agreement into two administratively independent and separate entities, the Federation of Bosnia and Herzegovina, FB, and the Republika Srpska, RS, affects regulatory control in the area of health and the environment, including ionizing radiation, which comes under the remit of the Ministries of Health. INFB work began in 1997 with the assistance of the IAEA for the preparation of a new legal framework consistent with the new political and administrative situation and in line with the IAEA's International Basic Safety Standards, IAEA, 1996. The new law on radiation protection and radiation safety, establishing the bases for the new regulatory system, was approved by Parliament in 1999. However, the modification and updating of existing regulations necessary for the practical implementation of the law are still ongoing. According to the new law, the regulatory powers and responsibilities for radiation and waste safety are attributed to a Federal Administration for Radiation Protection and Radiation Safety, FRPA, FB, an independent department within the Ministry of Health. The FPRA mainly has regulatory responsibilities but also carries out a number of operational tasks, such as personal dosimetry, radioactive waste management, and emergency management. FRPA receives technical support from the Center for Radiation Protection of the National Institute of Public Health, CRP. 260. Post-conflict environmental assessment. IAEA assessment. Because of the division of the country into two administratively separate entities, FI and RS, the legal framework currently developed in FI is not applied in the RS. Similarly, the FRPA only has authority in the FB. The regulatory structure in the RS is similar to the one in place in the FB, with a Radiation Protection Department operating within the Public Health Institute, which is part of the Ministry of Health. However, the FB has received support from the IAEA since the end of the conflict, whereas the RS has only recently benefited from the IAEA's assistance programs. Consequently, the radiation safety infrastructure in RS is less developed than in FI and still inadequate to deal with the requirements of the implementation of a safety regime. M.2.2 Radioactive sources and radioactive waste safety in BiH. Although there are no nuclear facilities in BiH, a large number of radioactive sources and radiation generators previously existed in the country. These were used in medicine, diagnostic radiography, cancer radiotherapy and nuclear medicine, industry, industrial radiography, research and teaching establishments. Radioactive lightning rods and smoke detectors were also commonly used in the country. The IAEA has estimated that the inventory of radioactive sources and radiation generators was as follows. 430 diagnostic X-ray machines used in medical and dental practices, more than 20 radioactive sources used in radiotherapy, 5 nuclear medicine laboratories, 40 X-ray machines used in industry, between 120 and 150 radioactive sources used in industry, 26 radioactive sources used in defectoscopy, non-destructive testing, 535 radioactive lightning rods, and about 30,000 radioactive smoke detectors. During the war, a large number of these sources were destroyed, damaged, lost or removed without proper registration. Afterwards, only a limited number of new sources were acquired, including a new Co-60 source for a teletherapy unit and some of 192 sources for industrial use. M. One of the priorities of the new regulatory body created in the aftermath of the war was the identification, recovery and, whenever necessary, safe storage or disposal of these sources. This issue is of high urgency because of the risks associated with the potential exposure to these sources of workers engaged in the reconstruction or repair of damaged buildings and facilities containing these sources, or of the general public who could come in contact with sources or their parts. In many cases, the IAEA found that insufficient attention was given to the protection of people, repair workers, rescue teams, members of the public, who could be inadvertently exposed to radiation and/or contamination by these sources. Considerable effort was made by the FRPA, with the assistance of the IAEA, to tackle this problem. In January 1997, the IAEA initiated an ad hoc project for radiation sources search and rescue in war-affected areas, with the participation of the CRP of the FBI and the Hazardous Waste Management Agency, UPO, of Croatia. The situation, however, remains far from being satisfactory. Although comprehensive records of the sources existed before the war, the new National Registry of Sources is still incomplete, with confusing and inconsistent data still needing to be clarified. The lack of collaboration between the two regulatory bodies in FBI and RS makes it practically impossible to have a complete picture of the current inventory of sources over the whole BIH. According to the information provided to the IAEA in 1999, roughly 60% of the sources depleted uranium in Bosnia and Herzegovina. 261 m. identified in the FBI were entered into the national inventory kept at the CRP. The validity of this estimate is questionable, as the numbers for some types of sources, lightning rods, smoke detectors, given for the FBI are the same as the total number of those sources existing in the whole of BIH before the war. Furthermore, other information indicated that a substantial fraction, if not the majority, of those sources were, in fact, in the territory which is now part of the RS. Due to the current absence of nuclear installations, no significant amount of radioactive waste from regulated practices is generated in BIH. The only radioactive waste produced comes from the disposal of obsolete radioactive sources, particularly the large numbers of lightning rods and smoke detectors. The safe storage of these sources is therefore the main priority of the CRP in the area of radioactive waste. Shelling during the war had damaged the radioactive storage facility that had previously been used for these purposes for 15 years. An inspection by the IAEA shows that the building was unsafe in view of the gamma radiation levels inside and around the storage facility and of the risk of contamination spreading to the surrounding populated area in the event of an accident. The selection of an adequate waste storage facility to replace the old one was an important part of early IAEA activities in support to the FBI. The two possible sites originally suggested by the CRP, a former WI bunker located within an industrial site of the Energoinvest complex and an old, unused railway tunnel 35 kilometers south of Sarajevo, could not be converted due to opposition by the workers at the industrial site and the significant investment involved to convert the railway tunnel into a radioactive storage. In the end, the authorities decided to build a new, interim low-level radioactive waste storage facility in a police complex in the vicinity of the Sarajevo airport, a few kilometers outside the city center. The interim waste storage facility was completed in 2000 and is now operational. M.2.3 Control of public exposure to radiation. Control of public exposures, through an environmental monitoring program, is one of the responsibilities of the new regulatory body, FRPA. The Institute of Hygiene and Environmental Protection of the Medical Faculty in Sarajevo have carried out some environmental monitoring activities, whereas the Department of Radiology of the Veterinary Faculty appeared to have carried out some control of foodstuffs. However, this area of work is affected by the same deficiencies: shortage of staff, inadequacy of resources, lack of regulations, that have hindered all activities of the CRP. With the exception of a limited amount of external radiation monitoring carried out at the university, No activities are carried out to ensure the protection of members of the public in areas accessible to them and where radiation and/or contamination risks may exist. This involves not only the possible exposure to sources used in hospitals or in industrial radiography sites, as in any other country, but also the higher risk of exposure to damaged, abandoned or uncontrolled sources as a result of the war disruption. M.3. Findings of the UNEP mission. M.3.1 Federation of Bosnia and Herzegovina. On October 16, 2002, the IAEA representative held a meeting with the Director of the Federal Administration for Radiation Protection and Radioactive Security in order to collect information on the overall situation related to radiation safety in the FB. During the meeting, the Director confirmed that work to strengthen the radiation safety infrastructure in order to comply with IAEA's international standards began just after the end. 262. Post-conflict environmental assessment of the conflict. He indicated that, since 1997, good collaboration had been established with the IAEA and that the initial shared activities focused on the management of sealed radiation sources in areas affected by the war. He added that substantial progress had been made towards establishing regulations complying with international standards as outlined in the IAEA Tech Doc 1067, IAEA, 1999, and that the next step would be implementation of regulations for exemption, notification and licensing of radioactive sources. The Director expressed regret for a lack of close collaboration with its counterpart in the RS. According to the administration, the most common radioactive sources found in the territory include sources used in hospitals for radiotherapy, CO-60 and brachytherapy sources, and nuclear medicine, lightning rods, containing EU-152, smoke detectors, as well as sources for industrial radiography, containing RA-192. The UNEP mission visited the FISO-level radioactive waste storage facility on October 22, 2002, accompanied by 2 staff members of the Department of Radiation Protection of the Federal Institute of Public Health. The recently built facility was found to be in very good condition and conforms to the current international safety standards for this type of facility. The staff working at the facility are being trained by the IAEA in areas related to the treatment and conditioning of radioactive waste, as well as radiation protection in general. The staff members appear to have sufficient basic knowledge and expertise to operate the storage facility in a safe and effective way. The building used as the storage facility is a concrete structure of fairly modest dimensions, approximately 4 meters long x 3 meters wide and 4 meters high. It is, for the time being, more than adequate for the current requirements of storing radioactive materials found in the territory of the FB, such as industrial radiography gauges, lightning rods, smoke alarms. An additional fence within the external perimeter fence around the complex encloses the construction. It is under constant police surveillance in order to restrict access. Dose rates measured at the fence are of the order of a few millisieverts per hour, microsieverts/H, rising to about 15 microsieverts/H in proximity of the building. No particular problems have been experienced by staff members when dealing with the radioactive materials located within the storage facility. Adjacent to the storage facility, a new building is under construction and will be used as a treatment and conditioning facility for radioactive waste. The construction has not yet been completed due to lack of funds. Authorities of the FI are seeking the technical and financial support of the IAEA to proceed with its construction. Once completed, this facility will provide a valuable contribution to the safe disposal of radioactive waste, and the authorities of the FI should be encouraged to direct their efforts at completing its construction. IAEA Assessment M.3.2 Republika Srpska. On October 18, 2002, the IAEA representative met with representatives of the Public Health Institute as part of the UNEP's visit to the Ministry of Health of the Republika Srpska, see Appendix L. The main counterpart at the meeting was the director of the Radiation Protection Department. The director provided information on the general institutional radiation protection structure within the RS and informed UNEP that legislation complying with IAEA's international standards for the protection against ionizing radiation was adopted in 2001. Resources, both financial and human, are limited, and the work of the Radiation Protection Department is mainly focused on the screening of X-ray machines. The department needs dosimeters and equipment to carry out environmental monitoring. According to the Public Health Institute, there are approximately 600 sources, including 250 X-ray machines, 5 quart machines, and approximately 50 dental X-ray machines, as well as sources for industrial radiography, lightning rods. Depleted uranium in Bosnia and Herzegovina. 263 m. And smoke alarms. The department carries out the inspection of these machines, but at the moment there is no operating facility for the storage of radioactive waste in the RS. In recent years, a fruitful collaboration has been established with the Vinca Institute of Nuclear Sciences in Belgrade, but legal difficulties prevent the return of some of these radioactive sources to the Vinca Institute. The preferred option by the authorities of the RS is the construction of a local storage facility for the safe disposal of low-level radioactive waste. A suitable site has been identified in an area under the control of the Army of the RS in the south of the country, but funds are needed to carry out the project. The Radiation Protection Department has benefited in the last couple of years from financial, technical and training support provided by the IAEA. In 2002, the department submitted 4 projects to the IAEA with a request for funds, and another proposal for the construction of a radioactive waste storage facility will be submitted in 2003. M.4. Storage of residues of depleted uranium in Bosnia. Throughout discussions with national authorities on the situation concerning the storage of radioactive waste in Bosnia, the UNEP team sought information on the recovery and storage of depleted uranium residues. The authorities indicated that no residues of DU had been recovered or were currently stored in any facility. At the end of the mission, fragments of DU penetrators found during UNEP's investigations of attacked sites were handed over to the authorities of the FI for their safe disposal. M.5. Conclusions and recommendations. 1. Commendable efforts have been made in establishing an institutional radiation protection framework in Bosnia since the end of the conflict. Considering the limited resources available, the achieved results are encouraging. Nonetheless, further effort is necessary in order to improve the radiation safety infrastructure of the country. Bosnia is currently receiving technical support from the IAEA, through the program of the Technical Cooperation Department. Continued IAEA support should ensure that the radiation safety infrastructure of the country is strengthened. This program includes 8 national and 9 regional projects covering different aspects of radiation protection, including control and prevention of illicit trafficking of nuclear and radioactive materials, monitoring of radioactivity in the environment, management of sealed radiation sources in areas affected by war, and technologies for managing radioactive wastes. 2. The existence of 2 separate legal frameworks and regulatory authorities in the 2 entities in which Bosnia and Herzegovina was divided after the war, FI and RS, results in a duplication of services and activities which is particularly inappropriate in view of the shortage of resources available. The lack of cooperation between the 2 radiation protection organizations created is also cause for concern and negatively affects the establishment and implementation of an efficient radiation safety regime in Bosnia. The solution to this issue goes beyond the mandate of the IAEA. However, efforts should be made at the international level to foster a closer collaboration between the organizations responsible for radiation safety in Bosnia. 3. The low-level radioactive waste storage facility of the FI provides an adequate facility for the safe storage of radioactive waste in the territory of the FI, including depleted uranium residues. The facility has been recently built and meets the necessary technological requirements for the safe storage of radioactive waste. The storage facility is surrounded by a fence and is located within police property under constant surveillance. Access to the area is restricted. All these measures guarantee that good control is exercised. 264. Post-conflict environmental assessment. Over the facility. The completion of the treatment and conditioning facility for radioactive waste next to the storage facility will improve the capability of the Center for Radiation Protection to deal with radioactive waste. Unfortunately, no storage facility for low-level radioactive waste is currently operational in the Republika Srpska, although progress has been made to identify a possible location where the facility could be built. The authorities indicated that they will seek the technical and financial support of the IAEA to proceed with the construction of a storage facility. The effort of the authorities of the RS in completing this project should be encouraged and supported by the IAEA. 4. The issue of the storage of DU residues in BIH should be dealt with the wider context of the safe disposal of radioactive waste within the country. Priority should be given to the storage and eventual disposal of obsolete radioactive sources, such as industrial sources, lightning rods and smoke detectors. Efforts should be directed particularly at the recovery and safe storage or disposal of the significant number of radioactive sources remaining, which were lost or damaged during the war. The risks from potential exposure to these sources are significantly higher than those from exposure to DU residues. Nevertheless, the authorities should be alerted to the presence of residues of depleted uranium on the territory of BIH and made aware of the remedial actions proposed by the UNEP mission. 5. While normal environmental monitoring is not a high priority for BIH where there are no significant sources of radioactive discharges from facilities, the problem of monitoring radiation and radioactive contamination in areas affected by the war is a severe one and it necessitates particular attention in view of the risk of potential exposures. IAEA assessment. Depleted uranium in Bosnia and Herzegovina. 265. N. Appendix N. Military use of DU. N.1 Military sources of depleted uranium. Depleted uranium has multiple uses by military forces. One of its uses, as in the civilian sector, is to serve as counterballast in both aircraft and missiles. However, not all counterballasts are made of depleted uranium. Because of its high density, 19.0 grams/cm3, and resistance to penetration by anti-armor munitions, depleted uranium can also be used in the armor of tanks, although not all tanks have depleted uranium armor. Depleted uranium is also used in anti-armor munitions and has several properties that make it ideal for this purpose. For example, when a depleted uranium penetrator hits armor, the rod begins to self-sharpen, thereby enhancing its ability to pierce the armor. Since DU is pyrophoric, during this self-sharpening the depleted uranium forms an aerosol, creating fine DU particles that may burn. The amount of depleted uranium which forms as an aerosol will depend upon the munition, the nature of the impact, and the type of target, that is whether it is an armored vehicle or not. Both tanks and aircraft can fire depleted uranium munitions, with tanks firing larger caliber rounds, 105 mm and 120 mm, and the aircraft firing smaller caliber rounds, 25 mm and 30 mm. Many of the world's armies possess, or are thought to possess, DU munitions. Rand, 1999. Depleted uranium munitions are conventional weapons and have been used in warfare. As such, these munitions are readily available on the open market to other armies. Munitions containing DU were used in Iraq during the 1991 Gulf War, as well as in Bosnia and Herzegovina, in 1994-1995. In the 1999 Kosovo conflict, NATO A-10 aircraft also used 30 mm DU munitions at targeted sites, and depleted uranium munitions were fired at sites in southern Serbia and Montenegro. NATO confirmed that over 30,000 rounds of DU had been used in Kosovo, more than 2,500 rounds in Serbia and 300 rounds in Montenegro, UNEP, 2000. In BIH, NATO information states that the numbers of DU rounds fired at any one target range from 120 to 2,400, with a total number of confirmed rounds standing at 6,230. Although the exact number remains unknown, see Appendix P. According to NATO/KFOR information provided to UNEP, the mixture comprised 5 DU rounds per 8 fired, KFOR, 2000. Nothing indicates that a different mixture was used in BH. The effectiveness of DU in kinetic energy penetrators, the rods of solid metal used as munitions, has been repeatedly demonstrated at various test ranges and in actual military conflicts. Kinetic energy penetrators do not explode, but, if they hit an armored, hard, target, they may form an aerosol of fine particles. Since uranium metal is pyrophoric, the DU particles ignite and burn, forming small particles of uranium oxides due to the extreme temperatures generated on impact, greater than 1000 degrees Celsius. Most of the contamination remains inside any vehicle that has been struck and penetrated, although some of the dust will be dispersed into the air and deposited on the ground of the surrounding environment. Importantly, DU hits on soft targets, for example non-armored vehicles, do not generate significant amounts of dust. Most DU dust from hard target impacts remains within roughly 100 meters of the target, 90% of which is expected within 50 meters of the target, CHPPM, 2000. Most penetrators that hit non-armored, soft, targets will pass right through the target and, in most cases, remain intact. A penetrator that hits the ground usually also remains intact and will continue down into the soil. The depth depends on the mass of the penetrator, the flight angle of the round, the speed of the tank or plane, and the type of soil. In clay penetrators. 266. Post-conflict environmental assessment. Used by the NATO A-10 aircraft have been reported to reach more than 2 meters in depth. Penetrators hitting hard objects, such as stones, may ricochet and may thus be found on the surface of the ground several meters from the attack target. As 7 years had elapsed between the conflict and the DU assessment mission, the major interest of the UNEP mission to BH was to examine the possible risks from DU to ground, water, beta and populations near the impact sites after such a period of time. N. The type of DU munition that the NATO A-10 aircraft uses has a conical DU penetrator. Its length is 95 mm and the diameter at the base 16 mm. The weight of the penetrator is approximately 300 grams. The penetrator is fixed in an aluminium jacket, also called casing, with a diameter of 30 mm and a length of 60 mm. The penetrator and jacket fit tightly through the cylindrical bore of the barrel of the A-10's Gatling gun, and the jacket assists the round in flying straight. When the penetrator hits a hard object, for example the side of a vehicle, the penetrator continues through the metal sheet, but the jacket does not usually penetrate. Military use of DU. The NATO A-10 aircraft is equipped with one Gatling gun. This gun can fire 3 900 rounds per minute. A typical burst of fire occurs for 2 to 3 seconds and involves 120 to 195 rounds. The shots will hit the ground in a straight line and, depending on the angle of the approach, the shots will hit the ground from 1 to 3 meters apart and occupy an area of about 500 square meters. The number of penetrators hitting a target depends upon many factors, including the type and size of the target. On average, not more than 10% of the penetrators hit the target, CHPPM, 2000. It is important to note that not all A-10 attacks are done with DU munitions. These planes also carry bombs and are used for bombing runs independently of any DU attacks. UNEP has no information that depleted uranium was used in the cruise missiles fired by NATO forces, or that DU tank munitions were fired during the conflict in BH. The Yugoslavian authorities say that the FRY forces did not use depleted uranium. In a letter to the journal Health Physics, the U.S. Department of Defense Directorate of Deployment Health Support stated that Tomahawk, cruise, missiles used in combat and Apache, helicopter 30mm rounds do not contain depleted uranium, Gilpatrick, 2002. This letter was in response to a previously published article in Health Physics, which stated that DU in the warhead of the Tomahawk was an assumption that was probably not correct, Durandi and Pugliese, 2002. However, The journal editors allowed the assumption to stand as an extreme worst case. To the fate of DU in the environment. Normally, 10 to 35%, and a maximum of 70%, of the penetrator becomes an aerosol on impact, with a hard target such as a tank or an armored personnel carrier, APC, or when the DU dust accumulated inside the hit target catches fire. Rand, 1999. The DU concentrations, rather than the number of DU particles in various particle sizes, will drive the resultant human intakes in internal doses. A DU hit should be confirmed with a radiation detection instrument, since other types of kinetic energy penetrators, such as tungsten alloys, may also leave a black dust cover. The use of color of the dust cover, that is light yellow, is an unreliable indicator for the presence of DU and depleted uranium oxides. After an attack with depleted uranium munitions, DU will be deposited on the ground and other surfaces in the form of DU metal in pieces, fine fragments and dust. If the DU has caught fire, DU will be deposited as dust of uranium oxides. Most of the DU dust around the targets on the U.S. Nellis Air Force Range is reported to have been deposited within a distance of 100 meters of the target. Nellis, 1997. These have been used for a long time period as U.S. Air Force training targets. Most of the penetrators that impact on soft ground, for example sand or clay, will probably penetrate intact more than 50 centimeters into the ground and remain there for a long time. Penetrators that hit armored vehicles form an aerosol upon impact or ricochet. Bigger fragments and pieces of depleted uranium in Bosnia and Herzegovina. 267. N. DU are initially deposited on the ground surface. Through weathering, the smaller fragments and dust will gradually be transported into the upper soil layer by water, insects and worms. Wind, rainwater or water that flows on the ground may also transport the smaller fragments and DU dust. Depending on soil composition, some of the dust particles will adsorb onto soil particles, mainly on clay and organic matter, iron oxyhydroxides and or carbonates, and thus be less mobile. Due to the fluctuating chemical properties of different soils and rocks, the fate of DU in the environment varies. Penetrators that are buried in clay will remain intact and will not affect the surrounding soil and groundwater. If penetrators are buried in quartz sand, they will weather relatively fast and may migrate to nearby groundwater. Weathering of penetrators buried in residual soils depends on the type of bedrock. If the soil consists of weathered granite or acid volcanic rock, the environment will be acidic and the weathering will be fast. Acid rain will accelerate the weathering, since uranium is acid soluble. Once located, penetrators and large pieces of DU can be collected. Otherwise, the DU is removed by gradual leaching from rain and melting snow. This weathering process of DU is principally by corrosion into hydrated uranium oxide, UVI, that is soluble in water. Other possible uranium compounds have a lower solubility in water. However, various adsorption processes in soil may slow the migration of uranium through soil by several orders of magnitude, essentially making it immobile. Accordingly, it will take many years, perhaps several hundred years, before DU contamination migrates from the site. 268. Post-conflict environmental assessment. Appendix O. Data on uranium. O. Data on uranium. O.1 Physicochemical and radioactive characteristics. Integral of uranium exists in various physical and chemical forms. Table O.1. Uranium occurs naturally in the +2, +3, +4, +5, and +6 valence states, but it is most commonly found in the hexavalent form. In nature, hexavalent uranium is commonly associated with oxygen as the uranyl ion, UO22+. The specific gravity is 19.07 grams/cm3 and melting point 132 degrees Celsius. Table O.2. Table O.1 Physical data on uranium. Compound uranium, uranyl chloride, uranyl nitrate, uranium dioxide, uranium trioxide, uranium Vi, oxide. Cas number 7440 61 17791 26 6 36478 76 9 1344 57 6 1344 58 7 1344 59 8. Molecular formula. U Cl2O2UN2O8UU02U3U3O8. Table O.2 Physicochemical properties, Lied, 1992-93. Compound melting point, degrees Celsius, boiling point, degrees Celsius. U 1132. Cl2O2U 578. N2O8U 60.2. UO2 2878. UO3 decomposes to U3O8. U3O8 1150 decomposes at 1300 degrees Celsius to O2. 3818 decomposes 118 density at 20 degrees Celsius, G/cm3, 19.072.8 10.967.308.38. Water solubility, G/liter, insoluble 3200 soluble insoluble. Besides the use of uranium as fuel in nuclear power stations, it is also in some uranium compounds used as catalysts and staining pigments. Depleted uranium is also used for shielding against radiation as it is heavy and absorbs gamma radiation. Berlin and Rudel, 1986. Naturally occurring uranium, Natu, is a mixture of three radioisotopes of uranium, 234U, 235U, and 238U, all of which decay mainly by alpha emission, and some weak beta and gamma emissions. Cuthern and Lappenbus, 1983, Lied, 1992-93. Natural uranium consists almost entirely of the 238U isotope, with the 235U and 234U isotopes respectively comprising about 0.72% and 0.0054% by weight of natural uranium. Greenwood and Earnshaw, 1984, Table O.3. Depleted uranium in Bosnia and Herzegovina. 269. O. Table O.3 Composition of natural uranium by weight. U238 U235 U234 U235/U238 U234/U238. 99.2745% 0.7200% 0.0054% 0.0072555.54 E-5. Table O.4 Uranium 238 Series, ICRP, 1983. Isotopes existing in depleted uranium. Nuclide. Uranium 238 238U, thorium 234 234 Th, protactinium 234 meters 234 mPa, 99.84%, plus protactinium 234 234 pascals, 0.16%. Uranium 234 234U. Thorium 230 230 Th, radium 226 226 Ra, radon 222 222 Rn. Polonium 218 218 Po. Astatine 218 218 at 0.02%, lead 214 214 petabits 99.98%. Bismuth 214 214 Bi. Polonium 214 214 Po, 99.98%. Thallium 210 210 TL 0.02%, lead 210 210 petabits. Bismuth 210 210 Bi. Polonium 210 210 Po, lead 206 206 petabits. Type of decay. Half-life 4.468 109 years. Average emitted energy per transformation. Alpha energy MeV. Beta energy MeV. Gamma energy MeV 4.26, 0.010, 0.001, 24.1 d, 1.17 meters, 6.7 hours, 0.059, 0.820, 0.009, 0.013, 2.45, 105 years, 4.84, 0.013, 0.002, 7.54, 104 years, 4.74, 0.002, 1,600 years, 4.86, 0.007, 3.824 d, 0.02%, 3.05 meters, 1.6 s, 26.8 meters, 5.59, 6.11, 6.82 dash, 0.04, 0.291, 0.284, 19.9 meters, 0.04%, 1.64, 10 to 4 years, 7.83, 1.3 meters, 22.3 years, 5.01 d, 138.4 d, 5.40, stable, 0.648, 0.389 dash, 1.46, 0.047 dash, 270. Post-conflict environmental assessment. Table O.5 Uranium-235 Series, ICRP, 1983. Do. Nuclide. Type of decay half-life. Uranium-235-235U. Thorium-231-231Th. Protactinium-231-231 pascals. 7.04, 108 years. 25.52 hours. 3.28, 104 years. Actinium-227-227 AC. 1.38%, plus. 98.6%. 21.77 years. Thorium-227-227 Th, 98.6%, plus. Francium-223-223 Fr, 1.38%. Radium-223-223 Ra. Radon-219-219 Rn. Polonium-215-215 Po. Lead-211-211 petabits. Bismuth-211-211 Bi. 99.7%, plus. 0.28%. Polonium-211-211 Po, 0.28%. Thallium-207-207 Tl, 99.7%. Lead-207-207 petabits. Branch decay due isotopes existing in depleted uranium. 18.72 d, 21.8 meters, 11.43 d, 3.96 s, 1.78 10 3 s, 36.1 meters, 2.14 meters, 0.516 s, 4.77 meters stable. Average emitted energy per transformation. Alpha energy MeV. Beta energy MeV. Gamma energy MeV. 4.47. 0.048, 0.154, 0.163, 0.026, 5.04, 0.063, 0.048, 0.069, 0.016, 5.95, 5.75, 6.88, 7.52 dash. 6.68, 0.021 dash, 0.046, 0.391, 0.075, 0.454, 0.492, 0.106, 0.059, 0.133, 0.058, 0.053, 0.047. 238U decays through 14 steps to 206 petabits, that is stable, table 0.4, and 235U through 11 steps to 207 petabits, table 0.5. Among the decay products there are the elements 226 Ra, which is a highly radioactive alpha emitter, 214 Bi and 214 petabits that emit nearly all gamma radiation in the uranium series. In nature, for example in an unprocessed uranium ore, uranium is almost in radioactive equilibrium with all its decay products from the whole uranium series. Data on uranium. However, in the chemical process when uranium ore is processed to pure uranium, the decay products of 234U and 235U respectively remain in the waste product. Thus, immediately after uranium has been extracted, it only consists of 238U, 234U and 235U, 0.72%. After a few months the immediate daughter products of 238U, 234Th and 234 pascals and the daughter product of 235U, 231Th, will be in radioactive equilibrium with their parents. That means that pure uranium, after a few months, emits not only alpha radiation but also beta and some weak gamma radiation. Because 234U has a very long half-life, it takes a long time for 234U to reach radioactive equilibrium with 238U, more than 800,000 years. Similarly, because the first daughter of 234U, 230Th, also has a long half-life, it is a delay for the decay products of 230Th like 226 Ra and his daughters to reach equilibrium with 230Th, etc. Depleted uranium in Bosnia and Herzegovina. 271. Table 0.6 Composition of depleted uranium by weight, defined as U-235 as 0.2% by weight. The depletion level found to date into ammunition. 238U, 235U, 234U, 235U/238U, 234U/238U. 99.7990%, 0.2000%, 0.0010%, 0.0020001.00 E-5. Depleted uranium is uranium that is a residual product obtained from the production of uranium fuel for nuclear reactors. Most reactors need uranium with a higher concentration of 235U than found in natural uranium. The uranium to be used in the reactor, enriched uranium, usually has a concentration of 235U that is 3.5% or higher. This is achieved, at the enrichment process, by separation of the heavier 238U isotope from the less heavy isotopes of 235U and 234U. As a result of the enrichment process, large quantities of depleted uranium are obtained, which has a much lower concentration of 235U and 234U than in normal uranium. Table 0.6. The definition of DU varies. Certain definitions use U-235 less than 0.7%, the natural level of uranium, others less than 0.35%, and some less than 0.30% as depleted uranium. Table 0.7 The relation between the fraction X of DU of the total amount of uranium in a sample and the ratio R equals U-235/U-238 in the sample, DU being defined as 0.2% U-235. X 1x R equals U-235/U-238 in the sample M 1/R 0 1 0.00720 139 0.1 0.9 0.00673 149 0.2 0.8 0.00620 161 0.3 0.7 0.00567 176. 0.4. 0.6. 0.00515. 194. 0.5. 0.5. 0.00462. 216. 0.6. 0.4. 0.00410. 244. 0.7. 0.3. 0.00357. 280. 0.8. 0.2. 0.00305. 328. 0.9. 0.1. 0.00253. 396. 1.0. 0. 0.00200. 499. Depleted uranium is also used for shielding against radiation as it is heavy and absorbs gamma radiation. Berlin and Rudel, 1986. Based on the DU assessments in both Kosovo and Serbia and Montenegro, DU used in NATO munitions contains 0.2% 235U, UNEP, 2001, UNEP, 2002. In a mixture of natural uranium and DU, the ratio 235U/238U will vary as follows, Table 0.7. Assuming an amount mg, of uranium of which X is the DU component and 1X the natural uranium component. The ratio R equals 235U/238U in the amount DU defined as 235U equals 0.2%, is estimated by using the formula R equals 0.72 minus 0.52x 99.2745 plus 0.5255x. 272. Post-conflict environmental assessment. Table 0.8 The specific activity of some radionuclides of interest. Radionuclide. Occurrence natural equals N artificial equals A. Half-life, years. Specific activity, BQ/Mg radionuclide. 238U. N. 4.4689. 12.4. 236U. 2.3415E7. 2'400. 235U. N. 7.0388. 80. 234U. N. 2.445E5. 231'000. 239 A. N. 24,065. 2'300'000. 240 6,537. 8'400'000. 241 14.4. 3'800'000'000. 242 3.763 E5. 145'000. 244 8.26 E7. 657. There is a very small natural production of Pu-239 in uranium through neutron activation, fission and cosmic neutrons. O. Data on uranium. Table 0.9 Specific activity of the common radionuclides in depleted uranium, 0.2% U-235, in terms of activity, BQ, of a radionuclide per mg DU. Isotope. Chemical composition 1. Specific activity, BQ/mg DU. U-238. 99.7990%. 12.38. U-235. 0.2000%. 0.16. U-234. 0.0010%. 2.29. Th-234. Traces, decay product. 12.27. Pot 234 meters. Traces, decay product. 12.27. TH 231. Traces, decay product. 0.16. Sum. 39.42. The TH 234 is a parallel way in the decay chain of pot 234 meters Tu 234, but with only about 0.15% intensity. 1, Brown et al., 1986. Specific activity of 238U is 12.4 becquerels/mg, Table 0.8. In natural uranium, Natu, in which 99.8% is 238U by weight, 238U and 234U are assumed to be in activity equilibrium. That means that when saying the uranium activity is 12.4 becquerels, it means that 238U and 234U each has that activity. If all decay products in the 238U series are in equilibrium, down to 206 petabits, all have the same activity, that is in the example 12.4 becquerels/mg Natu. The activity of 235U in natural uranium, 0.7% by weight, is only 0.56 becquerels/mg natural uranium. Depleted uranium is very much less radioactive than the uranium found in nature, which is in radioactive equilibrium with 226 Ra and its highly radioactive daughter isotopes. The specific activities of the common radionuclides in depleted uranium are presented in Table 0.9. Depleted uranium in Bosnia and Herzegovina. 273. 0.2 dose conversion factors for uranium isotopes and for DU. Committed effective dose per unit intake, SV/BQ, of various uranium isotopes via ingestion and inhalation for members of the public. From European Union Council Directive 96/29/Euratom of May 13, 1996, laying down the basic safety standards for the protection of workers and the general public against the dangers arising from ionizing radiation, Official Journal of the European Communities, No. L 159, Volume 39. September 26, 1996. A equals year. Hg equals the committed effective dose per unit intake or unit inhalation, SV/BQ, for ingested or inhaled uranium by an individual in the given age group. F1 equals gut transfer factor, that is the fraction of an element directly absorbed from the gut to body fluids, through intake by ingestion or inhalation. Type F equals denotes fast clearance from lung. Type M equals denotes moderate clearance from lung. Type S equals denotes slow clearance from lung. As seen from the tables of this section, the dose factors for infants and newborn babies, 1A, are about a factor of 4 times higher than for adults, greater than 17A, in the case of inhalation, and even greater in the case of ingestion. Table 0.10 committed effective dose per unit intake via ingestion, SV/BQ, for members of the public. Uranium 238, half-life 4.47 109A. Half-life H1A. H greater than 1A. 4.47 109A. F1 0.040. Hg 3.417. F1 0.020. 12 Hg 1.217. 27 Hg 8.018. 712 Hg 6.818. 1217 Hg 6.718. Greater than 17 Hg 4.518. Uranium 235, half-life 7.04 108A. Half-life H1A. H greater than 1A. 7.04108A. F1 0.040. Hg 3.517. F1 0.020. 12 Hg 1.317. 27 Hg 8.518. 712 Hg, 7.110.8, 1217 Hg, 7.010.8, greater than 17 Hg, 4.710.8. Uranium-234, half-life 2.44105 half-life. H1A. H greater than 1A. 2.44105 F1 0.040. Hg 3.710.7. F1 0.020. 1-2 Hg 1.310.7. 27 Hg 8.810.8. 712 Hg, 7.410.8. 1217 Hg, 7.410.8. Greater than 17 Hg, 4.910.8. Table O.11 Committed effective dose per unit intake via inhalation, SV/BQ, for members of the public. Uranium-238, half-life 4.47 109A. Type: H1A. H greater than 1A. F1. Hg. F1. F. 0.0401.9160 0.020. M. 0.0401.2105 0.020. S. 0.0202.910.5 0.002. 1-2 Hg 1.310.6 9.410.6 2.510.5. 27 Hg 8.210.7 5.910.6 1,610.5. 712 Hg. 7.310.7 4.010.6 1.010.5. 1217 Hg. 7.410.7 3.410.6 8.710.6. Greater than 17 Hg. 5.010.7 2.910.6 8.010.6. 274. Post-conflict environmental assessment. Data on uranium. Uranium-235, half-life 7.04108 Type: H1A. H greater than 1A. F1. Hg. F1. F. 0.0402.010.6 0.020. M. 0.0401.310.5 0.020. S. 0.0203.010.5 0.002. 1-2 Hg 1.310.6 1.010.5 2.610.5. 27 Hg 8.510.7 6.310.6 1.710.5. 712 Hg. 7.510.7 4.310.6 1.110.5. 1217 Hg. 7.710.7 3.710.6 9.210.6. Greater than 17 Hg. 5.210.7 3.110.6 8.510.6. Uranium-234, half-life 2.44105 Type: H1A. H greater than 1A. F1. Hg. F1. F. 0.0402.110.6 0.020. M. 0.0401.510.5 0.020. S. 0.0203.310.5 0.002. 1-2 Hg 1.410.6 1.110.5 2.910.5. 27 Hg 9.010.7 7.010.6 1,910.5. 712 Hg. 8.010.7 4.810.6 1.210.5. 1217 Hg. 8.2 10.7 4.2 10.6 1.0 10.5. Greater than 17 Hg. 5.6 10.7 3.5 10.6 9.4 10.6. Table O.12 Effective Dose Coefficients, SV/BQ, for workers. Uranium-238. Type FMS. Inhalation F1. 0.02 0.02 0.002. Uranium-235. Type FMS. Inhalation F1. 0.02 0.02 0.002. Uranium-234. Type FMS. Inhalation F1. 0.02 0.02 0.002. Hg 1 micrometer 4.9 10.7 2.6 10.6 7.3 10.6. Hg 1 micrometer 5.1 10.7 2.8 10.6 7.7 10.6. Hg 1 micrometer 5.5 10.7 3.1 10.6 8.5 10.6. Hg 5 micrometers 5.8 10.7 1.6 10.6 5.7 10.6. Ingestion F1. 0.02 0.002. Hg 5 micrometers 6.0 10.7 1.8 10.6 6.1 10.6. Ingestion F1. 0.02 0.002. Hg 5 micrometers 6.4 10.7 2.1 10.6 6.8 10.6. Ingestion F1. 0.02 0.002. Hg 4.4 10.8 7.6 10.9. Hg 4.6 10.8 8.3 10.9. Hg 4.9 10.8 8.3 10.9. O. Table O.13 Compounds and F1 values used for the calculation of ingestion dose coefficients. Uranium. 0.02 0.002. Unspecified compounds. Most tetravalent compounds, for example, UO2, U3O8, UF4. Table O.14 Compounds, long absorption types and F1 values for the calculation of inhalation dose coefficients. Adsorption type F. F1 0.020. M. 0.020. S. 0.002. Compound. Most hexavalent compounds, for example, UF6, UO2F2 and UO2NO3 two less soluble compounds, for example, UO3, UF4, UCO4 and most other hexavalent compounds highly insoluble compounds, for example, UO2 and U3O8. Depleted uranium in Bosnia and Herzegovina. 275. O. However, the volume of air breathed and mass of food and water consumed per unit of time are much smaller for infants and newborn babies than for adults. ICRP Report No. 23 Report of the Task Group on Reference Man 1974. Therefore, with a given concentration, BQ/M3 or BQ, the intakes by adults and infants are not so different. Furthermore, in the case of inhalation of insoluble uranium aerosols, the biological half-life for a substantial part of the initial lung burden is very long, of the order of years. Table O.15 is an example of lung clearance after an intake of 100 becquerels 234 US 5 micrometers S particles by an adult. Assuming the same clearance rate for children, it is concluded that the major part of the dose is received when the child has grown up. Furthermore, in the case of long-term exposure, childhood accounts for a limited period of time. Table O.15 Lung clearance and integrated effective dose is a function of time. Example 234U. Time after inhalation of 100 becquerels U234, days 2-10 101 000 10.000. Remaining U234 activity in the lung, BQ 8.67.84.61.90.12. Received effective dose, SV 2.7.10.5.1.10.44.0.10.46.9.10.49.2.10.4. On the basis of the circumstances given above, it is assumed that the uptake and resulting doses are those given for adults, type S absorption, the most conservative, only. Tables O.16 and Table O.17 show selected committed effective doses per unit intake, SV/BQ, of various uranium isotopes and of depleted uranium, SV/mg, respectively. Table O.16 committed effective dose per unit of intake, SV/BQ. Isotope U-238, U-235, U-234. Ingestion SV, BQ 4.5 10.8 4.7 10.8 4.9 10.8. Inhalation SV, BQ 8.0 10.6 8.5 10.6 9.4 10.6. Table O.17 committed effective dose per unit of intake of depleted uranium, SV/mg. Mode of intake SV per mg intake of DU. Ingestion 6.7 10.7. Inhalation 1.2 10.4. This value is about 3 times larger than that used in UNSEER 2000 and referred to in this appendix because a more conservative clearance factor is used in this report. 276. Post-conflict environmental assessment. O.3 Uranium nuclides in the environment. Natural uranium exists in various concentrations in all parts of the environment. There are also some artificial contributions of uranium to the environment, for example by release in waste tailings from mineral exploration, emissions from the nuclear industry, the combustion of coal and other fuels, and the use of phosphate fertilizers that contain uranium. O. Soils and rocks. Natural uranium occurs in higher than average concentration in certain types rocks, for example some types of granites and some black shales, for example alum shale and Chattanooga shale, and various mineral deposits. Rosova et al., 1979, Lied, 1992-93, see Table O.18. Data on uranium. Table O.18. Natural uranium concentrations in common soils and rocks. Higher and lower concentrations occur occasionally, A. Kerbohm and Melander, 1997. Soils. Range, mg, kg. World average. 3. World range. 0.0175. Sand. 0.53. Clay. 1.8. Serbia and Montenegro at the sites visited by the UNEP mission. 110. Rocks. Range, mg, kg. World average. 3. Basic igneous rocks 0.13. Granite, normal. 26. Granite, uranium rich 840. Limestone. 0.23. Sandstones. 0.55. Chattanooga Shale, USA. 2080. Alum Shale, Sweden, 5300. Uranium ores of good 10'000 300'000 quality, 0.5 to 30% uranium. Range, BQ, kg 35 1905 35 10 112 120. Range, BQ, kg 35 130 2500 100 500 231 60 251 000. 603 700. 6.2 105 370 105. Reference UNSEER 2000 UNSEER 2000. UNEP 2001. Reference Kogan et al. 1971. Swanson 1960 Anderson et al. 1985. Uranium in rocks that are unaffected by weathering or dissolution by groundwater is normally in radioactive equilibrium with all its daughter products down to Pb206, See Table 0.10. However, this is usually not the case in weathered rocks and in soils where either uranium or radium may have been partly dissolved and leached from the minerals. 35 becquerels U/kg soil leads to, with the level of equilibrium of short-lived daughters existing in the ground, an external absorbed dose rate in air of 15 mg per hour, or 0.02 millisieverts per year, adjusted for N or occupancy factor 0.8 and 0.7 sieverts/g for conversion coefficient from absorbed dose in air to effective dose received by adults. Depleted uranium in Bosnia and Herzegovina. 277. O. Water. In a survey of 130 sites, approximately 3,700 samples, in Ontario, Canada, conducted between 1990 and 1995, the mean of the average uranium concentrations, range 0.05 to 4.21 micrograms/liter, detection limit 0.05 micrograms/liter, in treated drinking water was 0.40 micrograms/liter, 1996. Uranium concentrations of up to 700 micrograms/liter have been found in private supplies in Canada, Moss et al., 1983, Moss, 1985. The mean concentration of uranium in drinking water in New York City, USA, ranged from 0.03 to 0.08 micrograms/liter, Fison and Welford, 1986. A mean uranium concentration of 2.55 micrograms/liter was reported in drinking water from 978 sites in the USA in the 1980s, US EPA, 1990, 1991. The daily uranium intake from water in Finland has been estimated to be 2.1 micrograms, Kalos and Azikainen, 1980. The daily intake from drinking water in Salt Lake City, USA, is estimated to be 1.5 micrograms, Singh et al., 1990. On the basis of the results of the survey from Ontario, 1996, the daily intake of uranium from drinking water in Canada is estimated to be 0.8 micrograms. Average value of annual intake by drinking water is 0.04 milligrams of natural uranium, 500 liters water per year. Table 0.19 Natural 238 U concentrations in water. Water type. Fresh waters. Groundwaters Finnish values up to. Yugoslavian values at the sites visited by the UNEP mission seawater. Reference value for drinking water. Range, micrograms/L 0.1281 to 12,100 0.04 to 41. 0.02 to 1.8. 1 to 3.3 0.08. Range, MBQ, L1 to 91 to 140 150,000 0.5 to 510 0.2 to 22. Reference. UNSEER 1993 UNSEER 2000 UNSEER 1993 UNEP 2001. 12 to 40.51. UNSEER 2000. Air. In air, the total activity concentration of uranium is about 1 microbecal/m3 and the reported range for the USA is 0.9 to 5 microbecal/m3, UNSEER, 2000. Mean levels of uranium in ambient air have been reported to be 0.02 nanograms/m3 in Tokyo, based on a 1979 to 1981 survey, Hirose and Sugimura, 1981, and 0.076 nanograms/m3 in New York, based on 2 samples, each a composite of 2 weekly air filter collections, from 1985 and 1986, Fison et al., 1987. On the assumption of a daily respiratory volume of 20 cubic meters and a mean urban airborne concentration of 0.08 nanograms/m3, the daily intake of uranium from air would be about 1.6 nanograms. Tobacco smoke, from 2 packages of cigarettes per day, contributes less than 50 nanograms of inhaled uranium per day, Lucas and Marcon, 1970. Inhalation intake of natural uranium is near 0.6 micrograms per year. Effective dose caused by inhaled uranium. 0.3 microsieverts per year if all uranium daughters, except radon and its daughters, are in equilibrium. 5.8 microsieverts per year from uranium and its daughters as they are in air, major part caused by 210 petabits/2 TINPO. 0.02 microsieverts per year from 238U alone and 0.03 microsieverts per year from 234U alone. 278. Post-conflict environmental assessment. Data on uranium. Food. Uranium has been detected in a variety of foodstuffs. The highest concentrations are found in shellfish, and lower levels have been measured in fresh vegetables, cereals, and fish. The average per capita intake of uranium in food has been reported to be 1.3 micrograms/day, Feisner et al., 1987, and 2 to 3 micrograms/day, Singh et al., 1990, in the USA and 1.5 micrograms/day in Japan, Nozaki et al., 1970. In a review of naturally occurring sources of radioactive contamination in food, dietary intakes of 238U were found to range from 12 to 45 millibecquerels/day in several European countries, from 11 to 60 millibecquerels/day in Japan. The higher values were found in uranium mining areas, and from 15 to 17 millibecquerels/day in the USA. The average daily dietary intake was in the order of 20 millibecquerels, or about 4 micrograms. It was often difficult to determine whether these dietary intakes included intake from drinking water, and it was emphasized that intake from drinking water has sometimes been found to be equal to intake from the diet. Harley, 1988. In a study by Chang et al., 1993, the mean uranium concentration in 9 different beverages was 0.98 micrograms/liter, range 0.26 to 1.65 micrograms/liter, and the mean concentration of uranium in mineral water was 9.20 micrograms/liter. Landa and Council, 1992, performed leaching studies to determine the quantity of uranium leaching from 33 glass items and 2 ceramic items in which uranium was used as a coloring agent. Uranium-bearing glasses leached a maximum of 30 micrograms of uranium per liter, whereas the ceramic-glazed items released approximately 300,000 micrograms of uranium per liter. Average value of annual intake by food is 0.46 milligrams of natural uranium. Effective dose caused by ingestion of Nat2, by food and water, results in Nat2 0.3 microsieverts per year. Therefore, 33 becquerels/kg soil, each of 238U and 234U, leads to a total annual intake by food and water of 6.2 becquerels of both 238U and 234U each, which leads to an effective dose of 0.3 microsieverts per year from both 238U and 234U. O. Person's body. Average value of body burden is 30 micrograms of natural uranium, 360 millibecquerels each of 238U and 234U, assumed to be in equilibrium. Effective dose caused by Nat2, in equilibrium, 238U and 234U each contributing about 50%, in the body is 7.4 microsieverts per year. Total effective dose caused by all uranium daughters in the body from ingestion and inhalation is 110 microsieverts per year, except radon daughters inhaled. The main part is from 210 petabits/2 TINPO ingested. Urine. The average amount of uranium excreted in urine from natural sources is roughly 0.01 microgram per day. The analysis of exposed persons' uranium concentration in urine can be used as a monitor for internal uranium exposure. Biokinetic models exist that can be used to back-calculate past uranium intakes based on actual urine excretion, depending on the intake path and time elapsed. WHO 2001, Royal Society, 2002. If exposure is to DU and not natural uranium, it is also possible in principle to estimate DU intake by measuring the isotopic composition of excreted uranium. using high sensitivity. Depleted uranium in Bosnia and Herzegovina. 279. O. Mass spectrometric analyses, like ICP-MS or TEMS, can achieve this. However, international experts believe that reliable estimates of uranium isotope ratios in such urine samples using such techniques is still challenging and subject to a number of potential problems. Adequate sensitivity is probably achievable for samples taken up to 10 years or more after acute exposure to DO, but the uncertainties in the assessed intakes are likely to be quite large. O.4 Health Standards, Limits and Levels. O.4.1 Chemical Toxicity, Health Standards. Water. The WHO derived a guideline for drinking water quality of 2 micrograms of uranium per liter. This value is considered to be protective for subclinical renal effects reported in epidemiological studies, WHO, 1998. US EPA 1991 has 30 micrograms/liter as a limit for uranium in drinking water, EPA, 2000. This is a new standard, the reference being 65 Federal Register, FR, 76708, December 7, 2000. National Primary Drinking Water Regulation, Radionuclides, FR USPA, 2000. EU Council Directive 98/83/EC on the quality of water intended for human consumption requires the member states to monitor the concentrations of radionuclides in public drinking water, EU, 1998. If the indicative dose exceeds 0.1 millisieverts per year, the competent authorities shall investigate to identify the cause and to take justified precautions. For uranium, the reference concentration is 100 micrograms/L, EU, 2001. Oral intake. For oral intake, a tolerable daily intake, TDI, for uranium of 0.6 micrograms/kg body weight per day has been established by the WHO, 1998. The U.S. Agency for Toxic Substances and Disease Registry, ACTS, established an intermediate minimal risk level, MRL, of 2 micrograms/kg body weight per day, ACTS, 1999. AIR. The American Conference of Governmental Industrial Hygienists, AGHY, adopted the maximum permissible concentration of 0.2 mg/m3 for soluble and insoluble natural uranium in air. The short-term exposure limit for natural uranium in the air was set at 0.6 mg/m3, AGHY, 1993. The U.S. National Institute for Occupational Safety and Health, NIOSH, recommends a limit for insoluble uranium of 0.2 mg/m3 for chronic occupational exposure, and 0.6 mg/m3 for short-term exposure. When these occupational guidelines are converted for exposure of the general public, they are 0.05 mg/m3 for chronic exposure and 0.15 mg/m3 for short-term exposure. For soluble uranium, the levels are 0.5 mg/m3 and 10 mg/m3, respectively, NIOSH, 1994. The U.S. Agency for Toxic Substances and Disease Registry derived a MRL for chronic inhalation exposure of 8 micrograms/m3. 280. Post-conflict environmental assessment. O.4.2 Radio Protection, Recommendations, Limits and Action Levels. Doses. Background. The world average dose received by man from natural unavoidable radiation is estimated to be 2.4 millisieverts/year, UNSEER 2000. This dose includes exposure to terrestrial radiation from the ground and building material, cosmic radiation, radiation from potassium-40 in the body, ingested radioactive elements in food and water and inhaled radioactive elements in the air. Indoor radon and radon progeny is responsible for main part of this dose. Depending on where you live, the annual dose may lower or higher. UNSEER gives a range of 0.5 to 10 millisieverts/year. Locally, the exposure to individuals can result in much higher doses. ICRP recommendations, from ICRP 60, 1991 and ICRP 65,1993. Trivial dose for the public is below 10 microsieverts per year. The dose limit for the public from all man-made sources excluding medical and natural sources is defined as 1 millisievert per year effective dose. The dose constraint for a given source 0.1 to 0.3 millisieverts per year effective dose to the public, that is, the practice shall be planned to give doses far below that value. The dose limit for the public for exposure of the skin is defined as 50 millisieverts per year. The planning dose limit for a given source is 0.1 millisieverts per year effective dose to the public, that is, the practice shall be planned to give doses far below that value. Action levels for radon in dwellings are defined as 3 to 10 millisieverts per year. Action levels for workplaces are defined as 3 to 10 millisieverts per year. The dose limit for a worker is defined as 20 millisieverts per year effective dose as an average over 5 years. The dose limit for workers in a single year is defined as 50 millisieverts per year effective dose. The dose limit for workers for exposure of the skin is defined as 500 millisieverts per year. If expected doses are over 100 millisieverts, countermeasures to prevent these doses are mostly always justified. Actions are probably justified after a nuclear accident or an existing unsatisfactory de facto situation if doses 10 to 100 millisieverts are prevented. EU limits. According to Article 9 of the Council Directive 96/29 Euratom of May 13, 1996, which lays down basic safety standards for the protection of health of workers and the general public against the dangers arising from ionizing radiation, the BSS. The limit on effective dose for exposed workers shall be 100 millisieverts in a consecutive 5-year period, subject to a maximum effective dose of 50 millisieverts in a single year, EU, 1996. According to Article 10, the dose to a pregnant woman shall be as low as reasonably achievable and not exceeding 1 millisievert. These dose limits refer to exposure at work. Article 13 referring to dose limits for members of the public sets the maximum effective dose at 1 millisievert/year. This limit refers to exposure to artificial sources. Article 2.4 excludes from this limit exposure to natural levels of radiation. Data on uranium. EU Directive on Quality of Water. EU Council Directive 98/83/AC on the quality of water intended for human consumption requires the member states to monitor the concentrations of radionuclides in public drinking water, EU, 1998. If the indicative dose exceeds 0.1 millisieverts per year, the competent authorities. Depleted uranium in Bosnia and Herzegovina. 281. Shall investigate to identify the cause and to take justified precautions. For uranium, the reference concentration is 100 micrograms/L, EU, 2001. 0.4.3 Summarizing information on uranium, UNSEER in WHO reports. Activity of U-238 is 12.4 becquerels/mg. In natural uranium, Natu, in which 99.8% is U-238 by weight, U-238 and U-234 are assumed to be in activity equilibrium. That means that when saying the uranium activity is 12.4 becquerels, it means that U-238 and U-234 each has that activity. If all decay products in the U-238 series are in equilibrium, down to lead-206, all have the same activity. That is in the example 12.4 becquerels/mg Natu. The activity of U-235 in natural uranium, 0.7% by weight, is only 0.56 becquerels/mg natural uranium. Body burden 30 micrograms uranium, Natu, 360 millibecquerels each of U-238 and U-234, assumed to be in equilibrium. Effective dose 7.4 microsieverts per year caused by Natu, in equilibrium, U-238 and U-234 each contributing about 50%, in the body. Total effective dose 110 microsieverts per year caused by all uranium daughters in the body from ingestion and inhalation, except radon daughters inhaled. The main part is from Pb/Po210 ingested. Air. Concentration in air 1 microgram/m3 each of U-238 and 234, 0.08 nanograms m3, Na2. Inhaled 7 millibecquerels per year each of Na2, tilde 0.6 micrograms Na2. Effective dose caused by inhaled uranium. Minus 0.3 microsieverts per year if all uranium daughters, except radon and its daughters, are in equilibrium, minus 5.8 microsieverts per year from uranium and its daughters as they are in air, major part, caused by Pb/Po210, minus 0.02 microsieverts per year from U-238 alone and 0.03 microsieverts per year from U-234 alone. Normal dust load, 50 micrograms dust particles/m3. Natural uranium in soil, 35 becquerels/kg, equals 3 mg Na2/kg. Uranium in dust as in soil, dust expressed as 3 mg Na2, kg as the average of soil. That is 1.7 microbecquerels/m3 air. 35 becquerels U, kg soil leads to, with the level of equilibrium of short-lived daughters existing in the ground, an external absorbed dose rate in air of 15 ng per hour, or 0.02 millisieverts per year, adjusted for N or occupancy factor 0.8 and 0.7 sieverts/g for conversion coefficient from absorbed dose in air to effective dose received by adults. Ingestion. Ingested by food are 5.7 becquerels/year, 0.46 mg Na2 per year. The drinking water concentration is 1 becquerel/m3, 0.08 mg Na2/m3. Intake by water results in 0.5 becquerels per year, 0.04 mg Na2 per year, 500 liters water per year. Effective dose caused by ingestion of Na2, by food and water, results in Na2 0.3 microsieverts per year. Therefore, 33 becquerels/kg soil, each of U-238 and 234, leads to a total annual intake by food and water of 6.2 becquerels of both U-238 and U-234 each, which leads to an effective dose of 0.3 microsieverts per year from both U-238 and U-234. 282. Post-conflict environmental assessment. Appendix P. List of NATO coordinates. NATO unclassified. P. NATO coordinates. These coordinates were provided to UNEP in the preparation phase of the field mission and correspond to AT-10 employment of 30 mm DU munitions during Allied operations to knife flight, deliberate force, 1993-95. Site number 1. 2 3 4 5 6 7 8 9. Date 5th of August 94. 22nd of September 94, 30th of August 95, 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 30th of August 95. 5th of September 95. Target 76 mm at self-propelling gun. T-55 tank. Warehouse artillery, bunker 120 mm artillery. AAA mortar position had Sissi military repair facility. Rounds 860. 120 unknown 800. 10. 7th of September 95. Han Pijsk Army Storage. 700. 11. 7th of September 95. Han Pijsk Army Storage. 700. 12. 7th of September 95. Han Pijsk Army Storage. 500. 13. 7th of September 95. Hanpijskarmi storage. 500. 14. 9th of September 95. Hadzisi military repair facility. 350. 15. 9th of September 95. Hadzisi military repair facility. 350. 16. 11th of September 95. Hadzisi ammunition storage depot. 400. 17. 11th of September 95. Hadzisi ammunition storage depot. 400. 18. 11th of September 95. Hadzisi ammunition storage depot. 550. 19. 11th of September 95. Hadzisi ammunition storage depot. 550. NATO coordinates are also published at the following website: www.nato.info. Link. Location: 434,432 newtons 182,108 T. 435,237 newtons 181702 E. Vicinity Sarajevo. Vicinity Sarajevo. Vicinity Sarajevo. Vicinity Sarajevo. Vicinity Sarajevo. Vicinity Sarajevo. 434,932.7 newtons 181122.9 E. 440,522.0 newtons 185655.7 E. 440,525.1 newtons 185653.7 E. 440,527.2 newtons 185653.5 E. 440,539.6 newtons 185649.7 E. 440,540.0 newtons 185645.0 E. 440,522.0 newtons 185655.7 E. 440,525.1 newtons 185653.7 E. 440,527.2 newtons 185653.5 E. 440,539.6 newtons 185649.7 E. 440,540.0 newtons 185645.0 E. 440,539.6 newtons 185649.7 E. 440,540.0 newtons 185645.0 E. 440,540.3 newtons 185642.5 E. 440,539.6 newtons 185649.7 E. 440,540.0 newtons 185645.0 E. 440,540.3 newtons 185642.5 E. 434,939.1 newtons 181117.3 E. 434,939.1 newtons 181117.3 E. 4,348 newtons 1812 E. 4,348 newtons 1812 E. 4,348 newtons 1812 E. 4,348 newtons 1812 E. Depleted uranium in Bosnia and Herzegovina. 283. Q. Appendix Q. Units. C. Units. C equals System International Unites. C. Basic units: quantity, length, mass, time, amount of substance. Name: meter, meter, kilogram, second, mole. Symbol kg, s moles. C. Derived units. Derived quantity. Name. Activity: ionizing radiations, Becquerel. ABSORBEDDOSC, SPECIFIC. Gray energy, imparted, Kerma. Absorbed dose rate. Gray per second. Dose equivalent, ambient dose. Sievert equivalent, Directional dose equivalent, personal dose equivalent, organ equivalent dose. Dose equivalent rate. Sievert per second. Volume. Cubic meter. Symbol BQ equals 1/SG equals J, kg equals M2/S2G, S equals M2/S3, SV equals J, kg equals M2/S2. SV, S equals M2/S3 M3. See prefixes. Exponent, base 10, of decimal numbers, En equals 10n. 1018 1012 1061 1002 10 10 3 10 9 10 15. Factory 18 E12 E6 E2 E-1 E-3 E-9 E15. Prefix exacta megahectodecimilli nanofemto. Symbol ETMHDMNF. 1015 109103 101 10 2 10 6 10 12 10 18. Factor E15 E9 E3 E1 E-2 E-6 E12 E18. Prefix petagiga kilo gigacendi micro picoito. Symbol PGKDAC micro PA. 284. Post-conflict environmental assessment. Examples of units used in this report. BQ, kg and BQ, L. Becquerel per kg, specific activity millibecquerel per liter, activity concentration. Q. Microbecquerels/M3. Microbecquerel per cubic meter, activity concentration. CPS. Counts per second, count rate. D. Days. Units. eV. Electron volt, 1 electron volt equals 1.602177 E-19 joule. Usually expressed in keV, kilo. Electron volt, in the gamma spectrometry, and MeV, mega electron volt. In the alpha spectrometry. G/M2. Gram per square meter, for example contamination of a surface. G/M3. Gram per cubic meter, for example contamination of a volume. MSV. Millisievert, effective dose. NSV, H. Nano, 10⁹, sievert per hour, dose equivalent rate. SV, mg. Committed effective dose per unit of intake, in this depleted uranium report. SV, BQ. Committed effective dose per unit of intake. Micro-R, H. Microröntgen per hour. Unit formerly used for measurements of gamma radiation, 1 micro-R, H is equal to 0.01 microsieverts/H. L. Liter. Minutes. Minutes. Mg, kg. Milligram per kg, equal to ppm, part per million. Micrograms/kg. Microgram per kg, equal to ppb, part per billion. Mg, L. Milligram per liter, concentration. Micrograms/cm2. Microgram per square centimeter, for example contamination of a surface. Moles/L. Moles per liter, amount of substance per liter. ppm. Parts per million, 1 part per million is equal to 1 milligram/kg. ppb. Parts per billion, 1 part per billion is equal to 1 microgram/kg. Y. Year. Depleted uranium in Bosnia and Herzegovina. 285. R. Appendix R glossary. A-10. The A-10 Thunderbolt II is the first U.S. Air Force aircraft specially designed for close air support of ground forces. They are simple, effective and survivable twin-engine jet aircraft that can be used against all ground targets, including tanks and other armored vehicles. Its 30mm Go-8/A Gatling gun can fire 3,900 rounds a minute and can defeat an array of ground targets, including tanks. DO is fired using this gun. Some of their other equipment includes an inertial navigation system, electronic countermeasures, target penetration aids, self-protection systems, and AGM-65 Maverick and AIM-9 Sidewinder missiles. A-10 Thunderbolt 2. Activity. The number of nuclear transformations occurring in a given quantity of material per unit of time. The C unit of activity is the reciprocal second, S1, per second, termed the Becquerel, BQ. Activity concentration. Activity, BQ, per unit mass or volume. ISO 921 distinguishes between specific activity, see below, as the activity per unit mass and the activity concentration as the activity per unit volume. Acute biochemical effects. High exposure of radiation doses can cause noticeable, significant consequences such as symptoms of illness or damage to normal body functions. Absorbed dose, specific energy, imparted, kerma. The amount of energy deposited in a unit mass of biological tissue. The unit of absorbed dose is the gray, G. See also dose quantities. Alpha particle. A positively charged particle ejected spontaneously from the nuclei of some heavy radioactive elements. The charged particle is identical with a helium nucleus, but of nuclear origin. It comprises 2 neutrons and 2 protons, and has a mass number of 4 and an electrostatic charge of +2. On capturing 2 electrons it forms an atom of helium indistinguishable from any other helium atom. APC. Armored personnel carrier. Atom. The smallest particle of an element that cannot be divided or broken up by chemical means. It consists of a central core called the nucleus, which contains protons and neutrons and an outer shell of electrons. Background radiation. The order of radiation from which a member of the public is exposed to natural sources, such as terrestrial radiation from naturally occurring radionuclides in the soil, cosmic radia. 286. Post-conflict environmental assessment. Originating from outer space, and naturally occurring radionuclides deposited in the human body. Becquerel. C derived unit for activity, ionizing radiation, BQ. Beta particle. Charged particle emitted from the nucleus of an atom. A beta particle has a mass and charge equal in magnitude to that of the electron. The charge may be either +1, positron, or -1, negatron. R. Bioindicators. Lichens, bark, mosses, mushrooms, etc. Analysis of these samples can indicate the possible presence of DO as evidence of earlier or ongoing air contamination. Glossary. Careful measurements. This method was often used to complement the measurements derived from line-up service. It consisted of measurements made with the inspector beta/gamma instrument, involving more careful removal of any covering of dust, grass etc., and measuring over a longer time period, to detect any possible shielded beta radiation from localized ground contamination or even widespread contamination. Cleanup. See decontamination. Committed effective dose. Following an intake into the body of a radioactive material, there is a period during which the material gives rise to an equivalent dose to one or several organs and an effective dose to the whole body. The committed effective dose is the time integration of the effective dose rate. If the time interval is not specified, it is implied that the value is 50 or 70 years, as defined by the regulator or assessor. Confidence level. The range, with a specified value of uncertainty, usually expressed in %, within which the true value of a measured quantity exists. Contamination. 1. Radioactive substances on surfaces, or within solids, liquids or gases, including the human body, where their presence is unintended or undesirable, or the process giving rise to their presence in such places. Also used less formally to refer to a quantity, namely the activity present on a surface, or on unit area of a surface. The English language term contamination refers only to the presence of activity, and gives no indication of the magnitude of the hazard involved. 2. The presence of a radioactive substance on a surface and quantities in excess of 0.4 becquerels/cm2 for beta and gamma emitters and low toxicity alpha emitters, or 0.04 becquerels/cm2 for all other alpha emitters. This is a regulatory definition of contamination, specific to the transport regulations. Levels below 0.4 becquerels/cm2 or 0.04 becquerels/cm2 would be considered contamination according to the scientific definition. 1. Contamination point. Small area of localized depleted uranium, DU, surface contamination found by field beta measurements, typically at the point of a penetrator impact. Decay, radioactive. Transformation of the nucleus of an unstable nuclide by spontaneous emission of charged particles and/or photons. Depleted uranium in Bosnia and Herzegovina. 287. R. Decay chain or series. A sequence of radioactive decays starting with one nucleus, a radionuclide. The initial nucleus decays into a secondary nucleus or progeny nucleus that differs from the first by whatever particles were emitted during the decay. Decay product. A new isotope formed as a result of radioactive decay. A nuclide resulting from the radioactive transformation of a radionuclide, formed either directly or as the result of successive transformations in a radioactive series. A decay product may be either radioactive or stable. Decontamination. Cleanup of a site, area targeted with DU. Removal of radioactive contamination. Depleted uranium, DU. Uranium having a percentage of uranium-235 less than the naturally occurring distribution of U-235 found in natural uranium, less than 0.711 weight% U-235. Dose per unit intake, dose coefficient. The committed effective dose resulting from intake by a specified means, usually ingestion or inhalation, of unit activity of a specified radionuclide in a specified chemical form. For intakes, synonymous with dose coefficient. Unit, SV, BQ. Dose quantities. Absorbed dose, D. The fundamental dosimetric quantity D, defined as collective effective dose, S. The total effective dose S to a population. Committed effective dose, E. Committed equivalent dose, height. 288. Post-conflict environmental assessment. Effective dose, E, equivalent dose, height. R. Glossary. Organ dose. Dose rate. Absorbed dose per unit time. Although dose rate could, in principle, be defined over any unit of time, for example an annual dose is, technically, a dose rate. The term dose rate should be used only in the context of short periods of time. For example dose per second or dose per hour. DU round. Complete depleted uranium projectile, including jacket, casing and penetrator. Effective dose, SV. See dose quantities. Depleted uranium in Bosnia and Herzegovina. 289. R. Effective committed dose. See dose quantities. Fragment. Part of a broken depleted uranium, DU, penetrator or jacket, casing. Gamma particle. Short wavelength electromagnetic radiation of nuclear origin. Penetrating radiation. Gray. C. Derived unit of the absorbed dose, G. Half-life, radioactive, time required for a radioactive substance to lose 50% of its activity by decay. Each radionuclide has a unique half-life. HRICPMAS. High-resolution inductively coupled plasma mass spectrometry. A highly sophisticated analytical method used to analyze the isotopic composition of a sample. ICPMAS. Inductively coupled plasma mass spectrometry. Individual survey. Single individuals or groups of two individuals together conducted surveys by sweeping, as line-up survey, in predetermined directions and areas. This method was used in very special circumstances when very little was known about the precise areas of a given site within which DU had been used. Insignificant risk. Low level of contamination, of the same order of magnitude as the natural uranium level. Insignificant radiological risk. when the corresponding dose is below 1 mSv. Insignificant toxicological risk, when the corresponding concentration, intake are below WHO health standards, recommendations or guidelines respectively. Isotope, a nuclide having the same number of protons in the nuclei, and hence the same atomic number, but differing in the number of neutrons and therefore in the mass number. Isotopic concentration. Unit mass, for example mg, of an isotope, for example U-238, per unit mass or volume in which the isotope occurs. Jacket, casing, the non-DO part of a projectile, made of aluminum, that holds the DO penetrator. Line-up survey, inline survey. A number of people, most often 4-6, were lined up with 1-2 meters between each person. The group walked slowly forwards, maintaining their alignment with one another, while sweeping the instruments at ground level left and right perpendicular to the walking direction in such a way that approximately all the area was measured. The walking speed was 7 ± 2 meters per minute depending on the terrain. 290. Post-conflict environmental assessment. Localized ground contamination. A contamination, detectable mainly by analytical methods, around the source of contamination ranging over an area, usually not more than 200 by 200 meters. Natural background concentration. The concentration or level of a substance that is derived solely from natural sources, that is of geological origin, according to ISO 11074-1 1996. Nuclide. A species of atom characterized by the constitution of its nucleus. The nuclear constitution is specified by the number of protons, Z, number of neutrons, N, and energy content, or, alternatively, by the atomic number, Z, mass number A equals N plus Z, and atomic mass. To be regarded as a distinct nuclide, the atom must be capable of existing for a measurable time. Penetrator. The armor-piercing DO core of a DO weapon projectile. Pyrophore, pyrophoric. DO, particularly as powder, is pyrophoric, which means that it can ignite spontaneously with oxygen in the air at temperatures of 600 to 700 degrees Celsius. When DO burns, the high temperature oxidizes the uranium metal to a series of complex oxides, predominantly triuranium octoxide, UO, but also uranium dioxide, UO, and uranium trioxide, UO. 38. 2. 3. Qualified at random survey. After a briefing on what to expect, how to conduct the survey and where to search, team members were sent out to search for radioactivity in the environment. Radiation weighting factor, WR. A number by which the absorbed dose in a tissue or organ is multiplied to reflect the relative biological effectiveness of the radiation in inducing stochastic effects at low doses, the result being the equivalent dose. Values are selected by ICRP to be representative of the relevant relative biological effectiveness and are broadly compatible with the values previously recommended for quality factors in the definition of dose equivalent. Radioactivity. The phenomenon whereby atoms undergo spontaneous and random disintegration, usually accompanied by the emission of radiation. Radionuclide. A radioisotope or radioactive nuclide characterized by the constitution of its nucleus. Reference case. Definition on how it is assumed that the attack happened, how much DO is used in the attack, size of the contaminated area, human exposure to DO, use of the contaminated area in the future and possible long-term effects of DO. Reference level. Ground surface contamination of 10 grams DO/M2. Glossary. R. SFAR. NATO's stabilization force in BH. C equals System International unites. Sievert, SV. C derived unit of any of the quantities expressed as equivalent or effective dose. Depleted uranium in Bosnia and Herzegovina. 291. R. Significant radiological risk. A significant radiological risk is defined in this report as one where any expected radiation dose would be greater than 1 millisievert per event, or per year. Significant risk. When the exposure of DO is higher than applicable health standards. Significant toxicological risk. When the expected concentration or intake would exceed WHO health standards, recommendations or guidelines. Soil. The upper layer of the Earth's crust composed of mineral parts, organic substance, water, air and living matter, according to ISO 11074-1, 1996. Specific activity. 1. The activity per unit mass of a radionuclide. 2. The activity per unit mass or volume of the material in which the radionuclides are asymptotically uniformly distributed. The distinction in usage between specific activity and activity concentration is controversial. Some regard the terms as synonymous, and may favor one or the other, as above. ISO 921-11 distinguishes between specific activity as the activity per unit mass and activity concentration as the activity per unit volume. Another common distinction is that specific activity is used, usually as activity per unit mass, with reference to a pure sample of a radionuclide or, less strictly, to cases where a radionuclide is intrinsically present in the material, for example carbon-14 in organic materials, uranium-235 and natural uranium, even if the abundance of the radionuclide is artificially changed. Specific energy, imparted. C. Absorbed dose. Surface soil. The top layer, a few centimeters, of the soil. In this assessment, soil samples from the first 5 to 10 centimeters were taken. Undetectable DO contamination. Low-level DO contamination. Not possible to differentiate from natural uranium present in the soil. Below the detection limits of the field and/or laboratory methods used. Widespread contamination. A contamination of the ground surface may be either localized or widespread over a large area, depending on the properties of the aerosols and the prevailing meteorological conditions. Widespread contamination exists in the case where the contamination can be found over a couple of hundred meters from the source of contamination. 292. Post-conflict environmental assessment. Appendix S. References. 1. AG, 1993. Threshold limiting values for chemical substances and physical agents and biological exposure indices. Technical Affairs Office AG. Cincinnati, Ohio, USA. 2. Adamo, P., Violandi, P., Violandi, A., 1989. Contenuto di radionuclidi nel tallo di stereoqualon vesuvianum, Pers. ADS.IT.E. 7,173-176. 3. Agapov A.M., Novikov Gian and Pavlovsky O.A., 2001. Use of ammunition with depleted uranium in Yugoslavia. Journal Most, S. Petersburg, No. 43, April 2001, p.3033. In Russian. 4. Akerbun G. and Melliner H., 1997. Geology and Radon. In Durrani and Illicar. Radon measurements by H-track detectors. World Scientific, Singapore, 2149. 5. Anderson A., Dahlman B., G.D. and Snoll S., 1985. The Scandinavian Alum Shales. Geological Survey of Sweden. Avhandling Rockabsatser, near 56. 55 p. 6. Annual Book of American Society for Testing and Materials, ASTM, Standards, 1999a. Standard Practices for Sampling Water from Closed Conduits, Designation, D3370-95A. Volume 11.01, Water I, Water and Environmental Technology, ISBN 08031-2688-5, 255-265. 7. Annual Book of American Society for Testing and Materials, ASTM, Standards, 1999b. Standard test method for isotopic uranium in water by radiochemistry, designation, D3972-97. Volume 11.01, Water 2, Water and Environmental Technology, ISBN 08031-2688-3, 368-373. 8. Unspa L.R., Shen J.H., Phelps P.L. and Kennedy N.C., 1975. Resuspension and redistribution of plutonium in soils. Health Physics 29, 571-582. 9. Atstr, 1999. Toxicological Profile for Uranium, Draft for Public Comment. Research Triangle Institute for Agency for Toxic Substances and Disease Registry, Atlanta, USA. 10. Barbizzi S., Dezorzi P. Galas C., 2002. Metrologia e Conduzione del Cambiamento Ambientale. Tato_Misser, Anno 4, Near 57, Inserto, Augusta e Edizioni Mortesino. 11. Beckett P. J., Boilo L.J.R., Vidavan D., Richardson D.H.S. and Nibawari, 1982. Lichens and mosses as monitors of industrial activity associated with uranium mining in Northern Ontario, Canada, Part 2, Distance-Dependent Uranium and Lead Accumulation Patterns. Environmental Pollution 4B, 91-107. 12. Ballas D., Ma R., Bramall N., McLeod C. W., Chapman N. Ensite K., 2001, Airborne Uranium Contamination, as revealed through elemental and isotopic analysis of tree bark, Environmental Pollution Volume 144, Issue 3, 383-387. 13. Byzrov L.G., 1994. Radionuclide content in lichen thallus in the forests adjacent to the Chernobyl atomic power plant. The Science of the Total Environment 157, 25-28. 14. Lasky B., Stuckenbroker G., Lusky R., 1970. The Use of Uranium as a Shielding Material. Nuclear Engineering and Design, 13, 146-182. North Holland Publishing Company. 15. Lies A., Daneza P.R. and Burkhard W., 2003. Properties, Use and Health Effects of Depleted Uranium, DU, A General Overview. Journal of Environmental Radioactivity 64, 93-112. 16. Bagativ S.A., Gorshkov V.E., Tklia E.V. and Al Imovich N.N.com in 1995. The Method of Reconstruction of Air Activities Following a Nuclear Accident. Radiat. Prot. Dozim. 62-3, pages 139-149, 1995. 17. Boilo L.J.R., Beckett P.J., Lavoie P. and Richardson D.H., 1982. Lichens and mosses as monitors of industrial activity associated with uranium mining in Northern Ontario, Canada, Part 1, Field Procedures, Chemical Analysis and Interspecies Comparison. Environmental Pollution 4B, 6984. 18. Braby, F. 1995. Estimating the concentration of uranium in some environmental samples in Kuwait after the 1991 Gulf War, Apple. Rad. ISOT. 46-4, 217-220. 19. Bray, G., 1999-2000. Valutazione dell'Indice di Biodiversità dell'Igniti Alcunri dell'Ezio. Tesi di Laurea. Dip. Biologia Vegetale, Università La Sapienza. Roma. 20. Brown J. and Simmons J. S., 1995. Farmland. A dynamic model for the transfer of radionuclides through terrestrial food chains. In RBBR 273. HMSO, London. 21. Brown E., Firestone R.B., Shirley V., 1986. Table of Isotopes. Lawrence Berkeley Laboratory, University of California. John Wiley & Sons Incorporated, New York. 22. Brummett R.K. and Powell C.E., eds. 1992. Authors of Plant Names. Royal Botanic Gardens, Kew. 23. Berger M., 2002. UNEP Post-Conflict Assessment 2001, Serbia, Montenegro. Report of the Swiss team. Spies. Laboratory Report with 1 Annex. Switzerland. 24. Cantilope C. Indigato S., 2000. UC Civili e Militari dell'Uranio Impoverito, Problemi Ambientali e Sanitari. Adidel. 31 Congresso Nazionale Arab, Ancona, Set. 2000, References. S. Depleted uranium in Bosnia and Herzegovina. 293. S. 25. Cinci RM, 1999, L'utilizzo di musci indigeni dripanciati per valutare in micro e macro areola ricadute al suolo di elementi in track, proposte metodologiche, in Piscini C. In Salvati S. Editors, at a workshop bio monitoraggio della qualità dell'aria sul territorio nazionale, Roma, 26 November 27, 1998. ANPA, Seriati 2 1999, 241-263. 25 HN, ZS Selecting Indicators to Evaluate Soil Quality, Department of Agricultural Chemistry National Taiwan University Taipei, 10617, Taiwan Rock, August 1, 1999. 26. THPPM. 2000. Health Risk Assessment Consultation Number 26 MF 7555 OOD. Depleted Uranium Human Exposure Assessment and Health Risk Characterization in support of the Environmental Exposure Report. Depleted Uranium in the Gulf of the Office of the Special Assistant to the Secretary of Defense for Gulf War Illnesses. Medical Readiness and Military Deployments, OSAGLI Levels 1, 2, and 3 Scenarios, September 15, 2000. 27. Clause G. Enru C., 1985. Liconagda Occidenta Europo. Illustrita determine libro. Bull. Suck. Bot. Centralist, N. S., near spec. 7. 28. Cranston P. 2001. Migration de l'uranium dans un podzol. Le rôle des colloïdes dans la zone non saturée et l'UNEP, Application hollandaise de Gascogne. Ph. Doctor Thesis, University of Grenoble 1, France. 29. Crowdake I, Warwick P., Taylor R., D.S., 1998, Rapid Procedure for Plutonium and Uranium Determination in Soils using a borate fusion followed by ion exchange and extraction chromatography. Analytica Chimica Acta 371-1998217225. 30. Curry L.A., 1968. Limits for Qualitative Detection and Quantitative Determination. Anil. Chem, 40, 586-593. 31. Dobson F.S., 2000. Lichen. An Illustrated Guide to the British and Irish Species. The Richmond Publishing Co., 431 pp. 32. No. 2000. Exposure Assessment Project at the Paducah Gaseous Diffusion Plant. December 2000. http://www.a.do.gov benefits/docs/20012 paducah.pdf. 33. Duff, 2000. Depleted Uranium in the Gulf, 2. Environmental Exposure Report. U.S. Department of Defense. December 13, 2000. 34. Duranti and Pugliese, 2002. Duranti, M. and Pugliese, M. Estimates of Radiological Risk from Depleted Uranium Weapons, Health Physics 80-1, 1420, 2002. 35. ICP 1, 1996. Contamination on surfaces by resuspended material. European Commission. Experimental Collaboration Project No. 1. Final Report. €16,527 N. 36. Ericsson RL et al. 1990. A review of the environmental behavior of uranium derived from depleted uranium alloy penetrators. Pacific Northwest Laboratory, Richland, Washington. PNL 7213. 37. EU, 1996. Council Directive 96/29/Euratom of May 13, 1996 laying down the basic safety standards for the protection of workers and the general public against the dangers arising from ionizing radiation. Official Journal of the European Communities. L159. Volume 39. June 26, 1996. 38. EU, 1998. Council Directive 98/83/EC of November 3, 1998 on the quality of water intended for human consumption. Official Journal of the European Communities. L330 32. December 1998. 39. EU, 2001. Draft modification to OJL 330/46 of May 12, 1998, version March 13, 2001. Annex 2, Monitoring. 40. Euracom, CITAC Guide 2000. Quantifying Uncertainty in Analytical Measurement. 2nd edition, 2000. 41. European Commission 2001. Opinion of the group of experts established according to Article 31 of the Euratom Treaty. Depleted uranium. 42. Exploranium GS Limited, 1989. Portable Gamma Ray Spectrometer, Model GR256 with GPS 21 detector. Manual. Exploranium GS Limited, Bolton, Ontario, Canada. RFV. Number 4 to October 26, 1989. 43. Fuge GB, Niemann L. and Jankes, 1990. Lichen and Mosses, Silent Chronists of the Chernobyl Accident. Bibliotheca Lichenologica 38, 6377. 44. Ferry BW, Baddeley MS and Hawksworth DL, eds. 1973. Air Pollution and Lichens. University of Toronto Press, Toronto. 45. Food and Fertilizer Technology Center, 5F.14 Limco Street, Taipei 10616 Taiwan ROC www.hagnet.org Weblink image/ep473t6.html. 46. Galsam Izal, Letruit Galinuma, Deschamps C, Savandi, Adname M, Duclox G, 2000, Atmospheric Metal Deposition in France, Estimation based on Mass Analysis. First results. IAEA Tech Doc 1152, 108 115. 47. Garland J. A., 1979. Resuspension of particulate material from grass and soil. IRR 9452, London. 48. Garland J. A., 1982. Resuspension of particulate material from grass. Experimental Program. 1979 to 1980. ERR 10106, London. 49. Gardy J., Gallon M. and Kessel M., 1979. Localization of heavy metals and other elements accumulated in the lichen talus. New Phytologist 82, 159-168. 50. Gardy J., 2001. Biomonitoring Atmospheric Heavy Metals with Lichens, Theory and Application Critical Reviews in Plant Science, 24, 309-371. 51. Gillette, 1977. Fine Particulate Emissions Due to Wind Erosion, Trans. SAE. 52. Goldstein S. J., Rodriguez J. M. and Lujan N., 1997. Measurement and Application of Uranium Isotopes for Human and Environmental Monitoring. Health Phys. 72-1, 1018. 294. Post-Conflict Environmental Assessment. 53. Grodzinska K., Sharaklukaska G, 2001, Response of MOS to Heavy Metal Deposition in Poland, an Overview, Environmental Pollution 114-2001443451. 54. Guidelines for Drinking Water Quality. 2nd ed. Volume 2 Health Criteria and Other Supporting Information, 1996, pp. 940,949, and Addendum to Volume 2. 1998, pages 281 to 283, Geneva, World Health Organization. 55. Haas Jr., Bailey H. and Purvis O. W., 1998. Bioaccumulation of metals by lichens, uptake of aqueous uranium by Peltagra membranacea as a function of time and pH. American Mineralogist 83, 1494 to 1502. 56. Harley N. H., Folk C. C., Hilborn L. H., Hudson A., Anthony C. R., 1999. A review of the scientific literature as it pertains to Gulf War illnesses. Rand. Washington, USA. 1999. www.gulflink.ist.mil/weblink. 57. Hoffman W., Atarben, Leonard H. and Turk, R., 1993. 137 CS concentrations in lichens before and after the Chernobyl accident. Health Physics 64, 7073. 58. Hollander, 1994. Resuspension factors of CS-137 in Hanover after the Chernobyl accident. J. Aerosol Science, 25. 59. Homey. and Person BRR, 1978. Global fallout of curium. Nature, 273, 289-290. 60. IAEA, 1979. Gamma ray surveys in uranium exploration. International Atomic Energy Agency, Technical Report Series number 186. P90. 61. IAEA, 1996. International Basic Safety Standards for Protection Against Ionizing Radiation and for the Safety of Radiation Sources, Safety Series number 115, Vienna. 62. IAEA, 1999. Organization and implementation of a national regulatory infrastructure governing protection against ionizing radiation and the safety of radiation sources. Interim report for comment. IAEA Tech Doc 1067, Vienna. 63. IAEA, 1999. Report on the inter-comparison run for the determination of trace and minor elements in lichen material. IAEA 336 inches IAEA/L/079. NA-ERS 33. 64. IAEA, 2000. Biomonitoring of atmospheric pollution, with emphasis on trace elements, Biomap, June 2000, IAEA Tech Doc 1152. 65. ICRP, 1974. Report of the Task Group on Reference Band, 1974. Commission on Radiation Protection, ICRP, Publication Number 23. Pergamon Press, 1975. 66. ICRP, 1983. Radionuclide Transformations. Energy and Intensity of Emissions. Annals of the ICRP. ICRP Publication 38, Volume 1113, 1983. Pergamon Press. 1983. 67. ICRP, 1991. Recommendations of the International Commission on Radiological Protection. ICRP Publication Number 60. Pergamon Press 1991. 68. ICRP, 1993. Protection against Radon-222 at home and at work. Report of the International Commission on Radiological Protection, ICRP Publication Number 65. Pergamon Press 1993. 69. Idalchik, 1975. The Manual on Hydraulic Resistances. Moscow, Mashinostroyny Publ, in Russian. 70. ISO, Tech Guide 17025. General requirements for the competence of testing and calibration laboratories. American Association for Laboratory Accreditation, HULA. Frederick, Maryland, USA. 71. Jaron C., Bernay R. and Badak F., 1995. Transplanted epiphytic lichens as bioimiters of air contaminated by natural radionuclides around the Irevsky VHR uranium mine, Slovenia. Lichenologist, 27-5, 375-385. 72. Jaron C., Jasimovic R., Badak F., Smodis B. and Walter B. HTH, 1996. Atmospheric heavy metal pollution in Slovenia derived from results for epiphytic lichens. Fresenius Sterlanal. Chem, 354-681-687. 73. Gia G., Belli M., Rosa Amelia S., Guadino S. and Sanson U., 2002 B., a new method for determination of uranium isotopes in water, vegetation and soil by alpha spectrometry, proceeding of the International Congress on the Radioecology Ecotoxicology of Continental and Estuarine Environments, Aix-en-Provence, France, 3 September 7, 2001, Radio Protection, Colloques, Volume 37, C1 957-962. 74. Gia G., Belli M., Sanson U., Rosa Amelia S., Acone R., Guadino S., 2002 A. Determination of uranium isotopes and environmental samples by alpha spectrometry, Journal of Radioanalytical and Nuclear Chemistry, Volume 253, Number 3, 395-406. 75. Jovanovic S., 1995, An Experience in Montenegro with Atmospheric Pollution by Means of Lichens, J. Trace and Microprobe Techniques, 13-4, 1995, 463-471. 76. Junjic, Sasa, Jakovljevic, Branislava, Rakita, Ivka et al. Maligna obolginja uklinicum centrobomjaluka od 1993-2000 Godin. Report of the Kliniki centrobomjaluka, Klinika Onkologiu. In local language, no date. 77. Kashirin I.A., A. Irmakov, S.V. Malinovsky et al. 2000. Liquid scintillation determination of low-level components in complex mixtures of radionuclides. Applied Radiation and Isotopes, 53. 78. Keller M., Annette B., Berger M., Schmidt E., Wiki A., Wer C. H., Spies Laboratory in cooperation with Chambers G., European Parliament, Directorate General for Research, Working Paper, Scientific and Technological Options Assessment Series, Style 100 in 05-2001. Depleted Uranium, Environmental and Health Effects in the Gulf War, Bosnia and Kosovo. Web, www.europaurl.eu.int. 79. FAR. 2000. NATO, FAR Unclassified Release to UNMIC. Subject, Depleted Uranium, DU. FAR Headquarters, Film City, Pristina, Kosovo, September 17, 2000. 80. Gilpatrick, M.E., No Depleted Uranium in Cruise Missiles or Apache Helicopter Munitions, comments on an article by Gerongi and Pugliese, Health Physics 82-6, 904-905, 2002. References. S. Depleted Uranium in Bosnia and Herzegovina. 295. S. 81. Kogan R. M., Nazarevi. M. and Friedman S. H. D. 1971. Gamma Spectrometry of Natural Environments and Formations. Atmizat. Moscow, 1969. Israel Program for Scientific Translations. Jerusalem. P. 1337. 82. Kuksa, 1994. Southern Seas, Aral, Caspian, Azov and Black, under anthropogenic stress. St. Petersburg, Jiromedeoisat. In Russian. 83. Lewis DL 1996. Assessing and Controlling Sample Contamination. Principle of Environmental Sampling, 2nd edition, edited by Lawrence H. Keith. 84. Lewis DL 1996. Assessing and Controlling Sample Contamination. Principle of Environmental Sampling, 2nd edition, edited by Lawrence H. Keith. 85. Lindsley G.S., 1978. Resuspension of the Transuranium Elements, a Review of Existing Data. In RPBR 75. HMSO, London. 86. La P.S. Endodominasis v. 1996. Lichens as long-term biomonitors of air quality in central Italy. Acta Botanica Neerlandica 45, 563-570. 87. McLean J., Purvis O. W. and Williamson B. J., 1998. Role of lichen melanins in uranium remediation. Nature 391, 649. 88. MCNP, 2000. MCNP, a General Monte Carlo in-particle transport code. Version 4C. Los Alamos National Laboratory. April 10, 2000. 89. Muck W.G., and DeVries J.J., 2001. Environmental Isotopes in the Hydrological Cycle. Principles and Applications. Volume 1. IAEA. 90. Muller H., Gehring F. and Prohl G., 1999. Model Description of the Terrestrial Food Chain and Dose Module FDMT in Rhodos PV 4.0. Rhodos WG3TN 9917. 91. Musilek L., Seshek T., Lozinska J., Walter B. H.Th. 2000, Biomonitoring Air Pollution in the Czech Republic by means of tree bark. IAEA Tech Doc 1152, 189-196. 92. NA 60, 2001. Report on the NAT9 Quality Control Exercise on Uranium Isotopes in 2 Soil Samples. International Atomic Energy Agency, Department of Nuclear Sciences and Applications, Division of Human Health, Section of Nutritional and Environmental Studies. IAEA Report NA 60. 93. Nash K., Fried S., Friedman A. M. and Sullivan J. C. 1981, Redox Behavior, Complexing, and Absorption of Hexavalent Actinides by Humic Acid and Selected Clays. Environmental Science and Technology, 15, 834-837. 94. Nash Th3 and Virvivi, eds., 1988. Lichens, Bryophytes and Air Quality. Bibliotheca Lichenologica 30. 95. NATO EP 49. Sampling and Identification of Radiological Agents, Volume 2, Forensic. 96. NATO, Stanag 4590, EP 49. Sampling and Identification of Radiological Agents Handbook, SIRA Handbook. 97. Nellis, 1997. Resumption of use of depleted uranium rounds at Nellis Air Force Range. Target 6310. U.S. Army Corps of Engineers, Nebraska. Draft June 1997. 98. Nebo and Richardson D.H., 1981. Like as monitors of atmospheric deposition in atmospheric pollutants in natural waters. Ed. By S. J. Eisenrich, 339-88. Ann Arbor, Michigan, Ann Arbor Science. 99. Nemes P.L. and Barabagliar, 1999. Line Ikeda Perlutolitsodi like Neopifidi cum bioaccumulatory dimetli intractia in Piscini C. And Salvati S. Editors, Adi Workshop Biomonitoraggio della Qualità dell'Aria sul Territorio Nazionale, Roma, 26 November 27, 1998. Apot, Seriati 2 1999, 279-289. 100. Nemes PL and Purvis OW, 2002, Monitoring Lichen as Indicators of Pollution. Monitoring with Lichen, Monitoring Lichens, Guru Academic Publishers, 710. 101. Nimes P.L., 1987. I macrolishny Detalia. Chiaviana Latishper la Determination. Cortania. Adi Museo Freetly / Store Nat. 8, 101 220. 102. Nimes P.L., 2000. Checklists of the Lichens of Italy 2.0. University of Trieste, Department of Biology, IN2.02, http://biobs.univ.trieste.it/. 103. NIOSH, 1994. Pocket Guide to Chemical Hazards. U.S. Department of Health and Human Services, Public Health Service, Centers for Disease Control and Prevention, National Institute for Occupational Safety and Health. 104. Osagui, 2000. Depleted Uranium, Human Exposure Assessment and Health Risk Characterization in Support of the Environmental Exposure Report. Depleted Uranium in the Gulf of the Office of the Special Assistant to the Secretary of Defense for Gulf War Illnesses, Medical Readiness and Military Deployments, Osagui. September 15, 2000. Health Risk Assessment Consultation, Number 26 MF 7555 OOD. 105. Pavlovsky OA, 2002. External radiation as a factor of radiation exposure under the two contaminated areas. Preprint Ibarasno 2002-03, Moscow, 2002, in Russian. 106. Virvitori R., 1999, Licni cum bioindicatore della qualità dell'aria, Stato dell'arte in Italia, in Piccinini C. and Salvati S. Editors, Adi Workshop Biomonitoraggio della qualità dell'aria sul territorio nazionale, Roma, 26 November 27, 1998. And the, Seriati 2 1999, 97 122. 107. Purvis O.W., Coppins B.J., Hawksworth D.L., James P.W., Moore D.M., 1992. The Lichen Flora of Great Britain and Ireland. Natural History Museum Publications in the British Lichen Society, London, 710 pp. 108. Ragnar Ersdottir KV and Charlotte L., 2000. Uranium Behavior in Natural Environments. In Environmental Mineralogy, Microbial Interactions, Anthropogenic Influences, Contaminated Land and Waste Management. J. Cotter Howells J., Batchelder M. Campbell L. and Valsami Jones Z., eds. 333-377. Mineralogical Society of Great Britain and Ireland. 296. Post-Conflict Environmental Assessment. 109. Reeks, M.W., J. Reed and D. Hall, 1988. On the Resuspension of Small Particles by a Turbulent Flow. J. Phys. D. Apple. Phys. 21. 110. Resrod, 2001. User's Manual for Resrod version 6. Environmental Assessment Division Argonne National Laboratory. ANL/ed4, July 2001. 111. Ribeiro Guevara S., Aribe M.A., Cavallo S. and Roman Ross G., 1995. Elemental Composition of Lichens at Nahuelhuapi National Park, Patagonia, Argentina. Journal of Radioanalytical Chemistry 198, 2, 437-448. 112. Richardson DHS and Nibelari, 1980. Surface Binding and Accumulation of Metals in Lichens. In Cellular Interactions in Symbiosis and Parasitism. Ed. By C. B. Cook, P. W. Pappas and E. D. Rudolph, 7594. Columbus, Ohio, Ohio State University Press. 113. Richardson DHS and Nibelari, 1981. Lichens and Pollution Monitoring. Endeavor, 5, 127-133. 114. Richardson DHS, Beckett P.J. and Nibori, 1980. Nickel in Lichens, Bryophytes, Fungi and Algae. In Nickel in the Environment. Ed. By J. O. Nittigu, 367-406. New York, John Wiley. 115. Rosamelia S., Guadino S. and Gia G., 2003. Uranium isotopes in water samples collected in Bosnia-Herzegovina. Italian Agency for Environmental Protection and Technical Services, APOT, contribution to UNEP post-conflict in Bosnia-Herzegovina. Prot. apot.ambassador.lab. 0582003. 116. Rosamelia S., Guadino S., Gia G., Patti, S. Ruizi, Patti, Leon P., Belleria V., 2003. B. Bioindicators, APOT report. Italian Agency for Environmental Protection and Technical Services, APOT, contribution to UNEP post-conflict in Bosnia-Herzegovina. Prot. apot.ambassador.lab. 1512003. 117. Rosamelia S., Guadino S., Gia G., Barbizzi S., Ruizi S., L. Zucchini, F. Fornazier, 2003. A. Methodology and Quality Control, APOT report. Italian Agency for Environmental Protection and Technical Services, APOT, contribution to UNEP post-conflict in Bosnia-Herzegovina. Prot. apot.ambassador.lab. 1502003. 118. SE International Incorporated, 1999. Inspector User Manual. SE International, Incorporated, Summertime, Tennessee 38483, USA. 119. Sanson U., Barbizzi S., Belli M., Guadino S., Gia G., and Rosamelia S., 2002. Italian National Environmental Protection Agency, ANPA, contribution to the UNEP post-conflict assessment in Serbia and Montenegro. 2001. Prot. ANPA, Ambassador Lab. 60, 2002. 120. Sanson U., Barbizzi S., Belli M., Guadino S., Gia G., Rosamelia S., Stellato L., 2001. A. Uranio Impoverito, Lavenza del Misser. Tato_Misser, Anno 3, 201. 172-176. 121. Sanson U., Barbizzi S., Belli M., Guadino S., Gia G., Rosamelia S., Stellato L., 2001. B. Levels of depleted uranium in the soils of Kosovo. Radiation Protection Dosimetry, Nuclear Technology Publishing. Volume 97, Number 4, pages 317 to 320. 122. Sanson U., Daneza P., Campbell M., Acone R., Buddy A., Stellato L., Rosamelia S., Gia G., Guadino S., Barbizzi S. and Belli M., 2001, Radiocological Survey at Selected Sites Hit by Depleted Uranium Ammunitions During the 1999 Kosovo Conflict, The Science of the Total Environment. 281, 2001, 2335. 123. Sifimos Rat, 1969. Scintillation meter S.P.P.2 NF User Manual. Sifimo PHY, 5 Ruta Theater, 91884, Massy, France. 124. Sloof J.E. and Walter BKH.th, 1991. Patterns in Trace Elements in Lichens. Water, Air and Soil Pollution. 5758, 785-795. 125. Spies Laboratory, 2000. Depleted Uranium, Hintergrundinformation. 126. Spies Laboratory, Test Report No. U8 2003-003, Element Screening Analyses of Water Samples with ICP Mass Spectrometry. 127. Spies Laboratory, Test Report No. U8 2003-004, element screening analyses of total digested soil sample solutions with ICP mass spectrometry. 128. SPES Laboratory, Test Report No. NUC 2002-024, Determination of Uranium Isotopes in Soil Samples, HATSISI Tank Repair Facility, from the UNEP Field Assessment Mission 2002 in Beh. 129. SPES Laboratory, Test Report No. NUC 2002-025, Determination of Uranium Isotopes in Soil Samples, Lukovica Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 130. SPES Laboratory, Test Report No. NUC 2002-026, Determination of Uranium Isotopes in Soil Samples, Dobrosivas, T55 Tank Position, from the UNEP Field Assessment Mission 2002 in Beh. 131. SPES Laboratory, Test Report No. NUC 2002-027, Determination of Uranium Isotopes in Soil Samples, HATSISI Barracks and Ammunition Storage Area, from the UNEP Field Assessment Mission 2002 in Beh. 132. SPES Laboratory, Test Report No. NUC 2002-028/A, Determination of Uranium Isotopes in Soil Samples 0 to 5 cm, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 133. SPES Laboratory, Test Report No. NUC 2002-028/B, Determination of Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 134. SPES Laboratory, Test Report No. NUC 2002-028/C, Determination of Uranium Isotopes in Special Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 135. SPES Laboratory, Test Report No. NUC 2002-028/D, Determination of Plutonium and Neptunium Isotopes in 3 penetrators from the UNEP Field Assessment Mission 2002 in Beh. 136. SPES Laboratory, Test Report No. NUC 2002-028/E, Determination of the Uranium Isotopic Composition of 3 penetrators from the UNEP Field Assessment Mission 2002 in Beh. References. S. Depleted Uranium in Bosnia and Herzegovina. 297. S. 137. SPES Laboratory, Test Report No. NUC 2002-028/F, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 138. SPES Laboratory, Test Report No. NUC 2002-028/G, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 139. SPES Laboratory, Test Report No. NUC 2002-028/H, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 140. SPES Laboratory, Test Report No. NUC 2002-028/I, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 141. SPES Laboratory, Test Report No. NUC 2002-028/K, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 142. SPES Laboratory, Test Report No. NUC 2002-028/L, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Honpajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 143. SPES Laboratory, Test Report No. Nuke 2002-028/M, Determination of Extracted Uranium Isotopes in Profile Soil Samples, Han Pajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 144. SPES Laboratory, Test Report No. Nuke 2002-028/N, Determination of Uranium Isotopes in the Extraction Residues of Profile Soil Samples, Han Pajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 145. SPES Laboratory, Test Report No. Nuke 2002-028/O, Determination of Uranium Isotopes in Profile Soil Samples, Han Pajsk Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 146. SPES Laboratory, Test Report No. Nuke 2002-030, Determination of Uranium Isotopes in Soil Samples, Vogoska Ammunition Production Site, from the UNEP Field Assessment Mission 2002 in Beh. 147. SPES Laboratory, Test Report No. Nuke 2002-031, Determination of Uranium Isotopes in Soil Samples, Kalinovic Water Reservoir and Ammunition Destruction Site, from the UNEP Field Assessment Mission 2002 in Beh. 148. SPES Laboratory, Test Report No. Nuke 2002-032, Determination of Uranium Isotopes in Soil Samples, Foka Bridge, from the UNEP Field Assessment Mission 2002 in Beh. 149. SPES Laboratory, Test Report No. Nuke 2002-033, Determination of Uranium Isotopes in Soil Samples, Ustikolina Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 150. SPES Laboratory, Test Report No. Nuke 2002-034, Determination of Uranium Isotopes in Soil Samples, Palkaran Barracks, from the UNEP Field Assessment Mission 2002 in Beh. 151. SPES Laboratory, Test Report No. Nuke 2002-035, Determination of Uranium Isotopes in Soil Samples, Bielasnoka Plateau, Ammunition Liquidation Site, from the UNEP Field Assessment Mission 2002 in Beh. 152. SPES Laboratory, Test Report No. Nuke 2002-036A, Determination of Uranium Isotopes in Air Filter Samples from the UNEP Field Assessment Mission 2002 in Beh. 153. SPES Laboratory, Test Report No. Nuke 2002-037, Determination of Uranium Isotopes in IAEA Reference Material, Soil, Sea Water, Lichen and Seaweed. 154. SPES Laboratory, Test Report No. Nuke 2002-038, Determination of Uranium Isotopes in Water and Water Filter Samples from the UNEP Field Assessment Mission 2002 in Beh. 155. SPES Laboratory, Test Report No. Nuke 2002-039, Determination of Uranium Isotopes in Water Samples from the UNEP Field Assessment Mission 2002 in Beh. 156. Stevenson F.J. 1985. Geochemistry of Soil Humic Substances. In, Humic Substances in Soil, Sediments and Water. Eds. Aiken G.R., McKnight D.M., Warshaw R.L. and McCarthy P., John Wiley and Sons, pp 1352. 157. Susney.com in 1968. The Measurement of Atmospheric Radioactivity. World Meteorological Organization. Technical Note Number 94. WMO, Number 231.TP.124. Geneva, Switzerland. 158. Swanson V.E., 1960. Oil Yield and Uranium Content in Black Shales. Geological Survey, Professional Papers 356A. Washington. 159. Symposium, Incidence of Malignant Tumors in Bosnia and Herzegovina Population. Sarajevo, March 21, 2002. Editor-in-Chief Fajuk Konjadzic, Editorial Board, Ladislav Azagovic, Tsmil Razikovic, Jela Vasikrujic. 160. Taylor H.W., Hutchinson E.A., McInnes K.L. and Svoboda J., 1979. Cosmos 954, Search for Airborne Radioactivity on Lichens in the Crash Area, Northwest Territories, Canada. Science, NY, 205, 1383-1385. 161. The Royal Society, March 2002, The Health Effects of Depleted Uranium Munitions. Document 602. ISBN 0854035753. 162. Tremblay M.L., Fosselt D. and Madsa S., 1997, Localization of Uranium in Cladina rangifrina and Cladina mitis and Removal by Aqueous Washing, The Bryologist, 103 368 376. 163. Trialzi C., Nanas Marzano F. and Vag M., 1996, Important Alpha, Beta and Gamma emitting radionuclides in lichen and moss collected in different world areas. Analiti Chimica 86, 699 704. 164. USAPI, 1994. Health and Environmental Consequences of Depleted Uranium Used by the U.S. Army. Technical Report, June 1995. Army Environmental Policy Institute. Champaign, Illinois, 1994. 165. U.S. Army Material Command, 2000. Tank Automotive and Armaments Command, TACOM, and Army Material Command, AMC, Review of Transuranics, TRU, in Depleted Uranium Armor. 19th of January, 2000. Memorandum. ATTNMXF, Mr. Pittenger, 5001 Eisenhower Avenue, Alexandria, Virginia 223330001. 298. Post-Conflict Environmental Assessment. 166. US EPA, 2000. National Primary Drinking Water Regulations. Radionuclides Final Rule, Environmental Protection Agency. 40 CFP Parts 9, 141, and 142. December 7, 2000. 167. UK, 2001. The Health Hazards of Depleted Uranium Munitions. Part 1. The Royal Society. 2001. 168. UK, 2001. The Health Hazards of Depleted Uranium Munitions. Part 1. The Royal Society. 2001. 169. UK, 2002. The Health Hazards of Depleted Uranium Munitions. Part 2. The Royal Society. 2002. 170. UNEP and UNCHS, 1999, The Kosovo Conflict, Consequences for the Environment and Human Settlements. United Nations Environment Programme and United Nations Center for Human Settlements, Habitat. 171. UNEP, 2000. NATO confirms to the UN use of depleted uranium during the Kosovo conflict. Press release, March 21, 2000. 172. UNEP. 2001. Depleted uranium in Kosovo, Post-Conflict Environmental Assessment. UNEP Scientific Team Mission to Kosovo, 5th-19th of November 2000. United Nations Environment Programme, Geneva, March 2001. 173. UNEP. 2002, Depleted Uranium in Serbia and Montenegro. Post-Conflict Environmental Assessment in FRY, United Nations Environment Programme, Geneva, March 2002. 174. UNEP, UNCHS Balkans Task Force, BTF. 1999. The potential effects on human health and the environment arising from possible use of depleted uranium during the 1999 Kosovo conflict. A preliminary assessment. Geneva. October 1999. 76. 175. UNSEER 2000. exposures from natural radiation sources. United Nations Scientific Committee on the Effects of Atomic Radiation. 48th Session of UNCER, Vienna, 12 to April 16, 1996. Preliminary Report. Draft. 1999. 176. UNCER, 1993. United Nations Scientific Committee on the Effects of Atomic Radiation. Report to the General Assembly, with scientific annexes. New York. United Nations 54. ISBN 92-1-142200. 1993. 177. UNCER, 2000. Sources and Effects of Ionizing Radiation. United Nations Scientific Committee on the Effects of Atomic Radiation. Report to the General Assembly, with scientific annexes. Volume 1. United Nations, New York, 2000. ISBN 92-1-142238-8. 178. UNCER. 2000. Sources and Effects of Ionizing Radiation, Annex B. Exposures from Natural Radiation Sources. United Nations Scientific Committee on the Effects of Atomic Radiation. Volume I. Sources. 179. Vukotic P., Angelic T., Zekic R., Kovacevic M., Vasic V., Ristich N., 2001. Field searching for ground contamination from depleted uranium at K. Parsa, Montenegro. 2001, unpublished report. 180. Wagner G., 1995. Basic Approaches and Methods for Quality Assurance and Quality Control in Sample Collection and Storage for Environmental Monitoring. The Science of the Total Environment 176, 1995, 6371. 181. Wade T. D., Davis J. A., Payne T. E., Wachkunas G. A., and Suen, 1994. Uranium, Vi, Adsorption to ferrihydrite, Application of Surface Complexation Model Geochemica et Cosmochemica Acta, 58, 5465 5478. 182. WHO Geneva, April 2001, Depleted Uranium, Sources, Exposure, and Health Effects. WHO/SDE/PHE/01.1. 183. WHO, 1998a. Guidelines for Drinking Water Quality. 2nd edition. Addendum to Volume 2, Health Criteria and Other Supporting Information. World Health Organization, Geneva, Switzerland. 184. WHO, 1998b. Derived Intervention Levels for Radionuclides in Food. World Health Organization, Geneva, Switzerland. 185. WHO, 2001. Depleted Uranium. Sources, Exposure and Health Effects. Department of Protection of the Human Environment, World Health Organization. Geneva, April 2001. 186. WHO, 2002, www.who.int. 187. WHO. 1998. Guidelines for Drinking Water Quality. 2nd edition. Addendum to Volume 2, Health Criteria and Other Supporting Information. Geneva, Switzerland. 188. Wilkins B.T., Simmons J.R. and Cooper J.R., Project Managers, 1994. Assessment of the present and future implications of the radioactive contamination of the Irish Sea coastal region of Cumbria. National Radiological Protection Board. NRBBR 267. HMSO, London. 189. Williams, 1992. An exact solution of the Reeks-Hall resuspension equation for particulate flow. J. 190. Wirth, V. 1995. Dieflechten-Baden-Württembergs. Ulmer & Co., Stuttgart. 191. WISE, 202. WISE Uranium Project. www.antenna.nl web link. References. S. Depleted uranium in Bosnia and Herzegovina. 299. T. Appendix T. List of contributors. Members of the UNEP mission. Mr. Bekkel Havisto, Mr. Mario Berger, Mr. Andrew Robinson, Mr. Jan Olaf Snes, Mr. Gustav A. Kerblam, Mr. Ernst Schmid, Mr. Marcus Istner, Miss Sylvia Rose Amelia, Miss Stefania Guadino, Mr. Mark Allen Melanson, Mr. Oleg Pavlovsky, Mr. Konstantinos Potiriadis, Miss K. Vala Ragna Ersdottir, Miss Alison Hendry, Mr. Tiberio Cabayank, Mr. Carlos Dora, Mr. Matty Valton and Miss Caitlin Brannon. Chairman of UNEP Do Projects, Project Coordinator, UNEP Report Writer, UNEP Scientific Leader, Swedish Radiation Protection Institute, SSI, Technical Leader, Swedish Radiation Protection Institute, SSI, SPIES Laboratory, Switzerland, SPIES Laboratory, Switzerland, Italian Environmental Protection Agency and Technical Services, APOT, Italy, Italian Environmental Protection Agency and Technical Services, APOT, Italy, U.S. Army Center for Health Promotion and Preventive Medicine, USASHM, Nuclear Safety Institute, Russian Academy of Sciences, Greek Atomic Energy Commission, Environmental Geochemistry, University of Bristol, UK. Environmental Geochemistry, University of Bristol, UK. International Atomic Energy Agency, IAEA, World Health Organization, WHO, Security Advisor, UNEP Project Assistant, UNEP. Other contributors. Mr. Michael Williams, Miss Akiko Hariyama, Miss Nikki Maith, Mr. Peter Hull, Mr. Matti Jipotoknik. Press Officer, Grid Technical Support Design and Layout. UNEP Post-Conflict Assessment Unit. Mr. Henrik Slot, Mr. Bekkel Havisto, Mr. Pazzi Rim, Mr. Mario Berger, Mr. Dennis Brunn. Head of Unit, Chairman, Senior Policy Advisor, Project Coordinator. 300. Post-Conflict Environmental Assessment. Mr. Anukit Guy, Mr. Richard Wood, Mr. David Jensen, Mr. Olin Nordbeck, Mr. Mikko Halonen, Mr. Gabriel Roca, Mr. Jerka Komer Gozovic, Mr. Andrew Robinson, Mr. Alan Wittig, Mr. Fredrik Delbech. Project Coordinator, Technical Coordinator, Program Officer, Research Officer, Expert System Administrator, Administrative Assistant, Report Writer, Information Assistant, Project Assistant. SPIES Laboratory Contributors. Mr. Mario Berger, Mr. Stefan Roel and Mr. Hans Solly, Miss Ruth Holzer, Mr. Alfred Jacob. APOT Laboratory Contributors. Miss Maria Belli, Mr. Umberto Sensen, Miss Kuagangia, Miss Alessandra Patti, Miss Patriza Leon, Miss Sabrina Barbizzi, Miss Vanessa Belleria. University of Viterbo Contributors. Miss Serena Ruizi, Miss Laura Zucconi, Miss Francesca Fornazier. USACHM. Mr. David P. Alberth, Mr. John Collins, Mr. Gordon Laud, Miss France Throm. Radon Contributors. Mr. Alexander Sobolev, Mr. Alexander Rumikov. Depleted uranium in Bosnia and Herzegovina. T. 301. List of contributors. This report by the United Nations Environment Programme was made possible by the generous contributions of the governments of Italy and Switzerland. Further information. Copies of this report may be ordered from SMI, Distribution Services, Limited, P.O. Box 119, Stevenage, Hertfordshire, SG14TP, UK. Telephone, +44 1438748111. Fax, +44 1438748844. UNEP also has an online bookstore at www.earthprint.com. Further technical information may be obtained from the UNEP Post-Conflict Assessment Unit website at postconflict.unep.ch.